Everyone, should I just check the sound? It's okay?
Yeah, we can hear you great, Eduardo.
Likewise, thanks.
Great. Okay, good afternoon and good morning, everybody. I think we're ready to get started with day 3 of PyHEP 2021. So thanks everybody for connecting again for another day of the workshop series. And we're gonna kick things off today with a tutorial, which is coming to us in multiple parts from multiple speakers on high performance histogramming for high energy physics analysis. So without any further ado, we're going to kick it over to Henry and Co to kick things off. Sorry, Henry
I
or
think, sorry, I think
okay,
Henry is not here, so
okay.
I can start first.
Okay, that'd be fantastic. And
Yeah.
please go ahead.
Yeah, okay. Can you see my screen?
Yes, we can.
Okay, yeah, great. Yeah, as Henry is not here, maybe he will introduce his basic features of both the histogram and UHI later when he come in. Both the histograms development is very active. Currently, we are still contributing to it. For example, one of the most important features that we want to achieve is numbification. Number is a high performance. Number is a high performance Python compiler that uses the industry standard LLVM to allow a fully number-enabled event loop for analysis. Histogramming steps need to be implemented with number decorator. In this summer, we will investigate this to enable both the histograms field from inside the LLVM number loop without stepping through Python. We were able to make a faster event loop, thereby improving the performance of all projects that rely on both the histogram. And here is the pseudocode. Currently, we can achieve this. As you can see, the field is outside the number function. Our goal is to make this work. That is to make the hist field within the number function. Powered by both the histogram, a library of histogramming for analysis named hist comes out. Hist library provides useful shortcuts for plotting and profiles, including the following features. To participate, you can run the notebook via the binder link on top of this. Hist allow names for both the histogram axes. The names are unique identifier in a histogram, which are used to support useful features such as field and project. Especially, his design named hist to provide name shortcuts for the histograms that contain name axes. For example, here we can initialize some hist axis and use it to construct a histogram. As you can see, you can obtain the axis names and labels from the histogram. Hist allow named field by name based on the normal field of both the histogram, which is much safer and more readable. Hist has customized wrappers when displaying a Jupyter notebook and supports dark mode. For example, here is a 1D histogram, and here is a 2D histogram, and here is 3D. Besides the fancy wrapper, the users can explicitly obtain the data by plot and shown method. Let's try an example. Here we can try show. This is a histoprint, and we can also use a plot. Yeah, this is use matplotlib plot. Okay. Histogram indexing extends both the histograms UHI and provides high-energy physics users with handy accessing shortcuts. For example, to access the central element of the 2D histogram, we can do the following things. Note that this is supported by both the histogram and hist, but these accessing methods are only for hist. Besides, hist UHI also supports rebin for histograms with the complex number shortcut. For example, here is the original 2D histograms, and we can rebin it. As you can see, the bins are much wilder. Besides the standard construction method of boost histogram, HIST provides quick construction for users. The boost histograms construction looks like this, but here we can use the new operator to quick construct the histograms. And fill it and wrapper it. HIST stack is a newly development features in the latest version of HIST. A HIST stack holds multiple histograms into a stack whose axes are required to be matched. Here we can create a stack using the named HIST and named HIST copy. As you can see, this is the named HIST and this is named HIST copy. To demonstrate that the axes are required to be matched, let's change the project axis to another. Yeah, you can see the histogram axes don't match. And by passing into a HIST type argument, you can get the field histograms. One of the interesting example of stack is you can create a stack using by converting the histograms with string category access. For example, here you can create a 2D histograms with one axis regular and one string category axis. Here you can create the stack with two histograms. One named good and one named bad. Let's see. Here it is. Yeah, you can also get the field stack and field plot and the reversed plot. And you can get the histogram inside the stack. HIST allow users to read dictionaries or panda data frame directly into HIST. Here I use a data set and show the pie plot of the histogram of a CSV field. Yeah, here is the pie plot. There are some other interesting shortcuts of HIST. For example, we can get the density of an existing histogram via density method. We can get the profiles of our histograms with respect to one axis. If you want to know more about HIST library, welcome to our GitHub repo. Then let me pass my mic to my collaborator, Henry or Aman, to talk about HIST plans and both the histograms current status.
Okay, thank you. Sorry about that earlier. My audio is off, so we're just sitting there wondering what was happening. Okay, I will share my screen. Okay, and I will make that a little bit larger. All right, so I'll give you a little overview of sort of what happened in the mostly since the last PyHEP for boost histogram and the development of UHI. Just start here. So boost histogram 1.0 came out and it had some great features. One of the best features was the removal of Python 2.7 and 3.5 support. which means the other features, including easier subclassing and full static typing across the entire library, were actually obtainable with fewer lines of code than the 0.13 release. And then along with those things, quite a few features that were intended for 1.0 were also backported to the Python 2 branch, which included this simpler Pythonic metadata system. So you can now just set any attribute on a histogram or on an axis, and they just get passed along. It behaves as if they were just regular nice Python classes, but it happens to move them through the C++ computations as well. It gives you better access to the accumulator storages. So there's really easy ways to get access to those sorts of things like the values and variances without having to change what you're doing based on what kind of histogram storage you have. And of course, the plottable protocol, which we'll talk about a bit later. And there were lots of updates to various other tools that happened as part of the Boost histogram work. PyBind 11 and CI build wheel both received major updates as part of this push. The PyBind 11 and 2.6 has new CMake and setup tools helpers that were heavily based on the Boost histogram setup tools and CMake tooling. There's faster accumulation. So if you're writing accumulation in PyBind 11, it's 40% faster, and that was to help Boost histogram. We're pushing for Python 3.9 support, Universal 2 support for the new Apple Silicon, including 3.8, because Boost histogram had to support that, and much more. Let's take a little look at what a statically typed histogram gives you. So I'm just going to write a very simple little script here. I'm just going to import Boost histogram. I'm going to set up a single one-dimensional axis. I'm going to go ahead and just grab some values from that. And then I'm just going to go ahead and run the reveal locals command, which is a mypy command that will just show you what the current types of everything are. So we'll do that. And you'll see that the revealed types were H is a histogram and vals is a numpy. So it understood that this thing was returning a numpy array. And you see the new numpy 1.21 things there. We don't really do anything except any there yet. If I turn that off, it would then give me a pretty little green, no issues. Okay, so now let's try a couple of common mistakes. So one common mistake would be what if you accidentally did an int category here, for example, and forgot that you changed that. Well, MyPy will find that before you even run your code and tell you, hey, these things need to be integers because you're asking for an integer category here. Or for example, you could make a mistake in indexing and pass something that's not valid there. Boost histogram doesn't support strings in indexing, and you get an error. And in fact, since I didn't actually change this back correctly, you'll notice one of the benefits of this over tests. For one, I didn't have to write any tests, and two, I'm getting both errors, even though these are not in separate test cases. So normally you should be writing lots and lots of test cases because you only get one error per case, and then it just quits. But here I'm seeing all of the errors at the same time. Just to keep from writing too much, I'm going to go ahead and switch that back. And another example is you could misspell something. I saw somebody put as one of the most common errors they make, they mistype something. Well, MyPy is definitely really good at catching that. If it's statically typed code, it will tell you. In fact, it'll even suggest the correct thing if it's a close miss. So several of these things. So a lot of the common errors listed on that page were actually things that MyPy can catch very easily. So if you're using it, this will be much, this will sort of help you use it better before you actually have to write code. And there you go, back to no errors. All right, let's take a look at Boost histogram 1.1. This was released yesterday and adds a few exciting features. For one, it finally added the Python 3.8 Apple Silicon support that was missing for quite a while, but the very last official release of Python 3.8 last feature release actually added support for this, so we were able to add it kind of just under the wire. And then scaling and addition now affect the flow bins too. So that's when you do the scaling or addition shortcut, where you just multiply by a scalar. But sort of the big thing in there was this new experimental support for selections of category axes. So I'm just going to import Boost histogram into my notebook, because before I had it in my little script that I wrote out here. And then I'm going to make a new histogram that has this good, bad, and ugly. First time that you use this, you'll get a little warning saying that this is experimental and that removed bins are not being added to the overflow, but that may change. But you can see that I was able to pass a list in here and get just the 0th and the 2nd item from that. So this gives me the ability to reorder axes. Now I could put in a different list, a different ordering here, and we get a different ordering out. This also lets you select by names. Now, since you've already seen histogram, because I'm going second, I'm just going to try this with hist as well. So I'm going to import hist. I'm just going to go ahead and convert H to a hist because they're the same thing. So, oops, hist. Okay, and there you go. Now we have a hist. This works the same way, though actually in this particular case, we should probably print it so that we can, oh no, it's right here. We'll just look right there. So you can see we're doing the same thing. We still get the warning, but the warning is already, it only shows once. So, and in hist, we don't have to add these looks because it's obviously a string. There is no ambiguity there. So in hist, you can just, verbally putting the right number of brackets, you can just do that. And now I get bad, good, I get exactly this out. See dot axes. You see, I get exactly this out. That good when I do that. So this just works here. If this was an integer axis, you can only do this on categories. But if this was an integer axis, let's do say something that's obviously not indexes. Then this is still selection by position. And if you want to select by the values in it, then you use the J shortcut, just like you saw before. So 3J, 5J, we pick out the 3 and the 5 values. So that just works as well. Okay, so one of the other big changes that has happened is the addition of the UHI, the Unified Histogram Interface. And this is a statically typed protocol that allows you to plot histograms from any source. So this is supported by Boost Histogram. It's supported by hist, obviously, because this just adds to Boost Histogram. It's supported by Uproot 4. It's supported by PyHEP. It's supported by Histoprint. So, and hopefully there'll be more libraries here as well. Any of these libraries can plot anything from one of these other libraries without depending on each other. So you can just hand an uproot histogram directly to PyHEP or Histoprint or anything else that supports UHI, and that will just plot or work without having to convert it to a Boost histogram or a hist or anything else. Okay. And there is actually a PyPy library, PyPI library for this, and it has some helper functions and things. You don't have to depend on this at runtime at all, but if you'd like to, there are some nice handy features that are in the library. So feel free to check that out. But this is what this protocol looks like. So this is just a overview of the things that you're allowed to use. So you get a series of methods and a property here that you can use to get information about the histogram, and 2 properties. Values, variances, and counts are the value, variance. I think we need somebody to unmute or to mute. If admin could do that, please. Okay, so values, variances, and kinds. So this is the value, this is the variance in whatever that value is. And this is the counts, which is how many fills have been received or ineffective fills for weighted histograms. And then the kind tells you either count or mean. And then the axes is a sequence of axes. So you can index it and loop over it and stuff. Axes themselves have their own protocol, and they have a they can be indexed, and if they're indexed, they either return a tuple of upper lower bin, or sorry, lower upper bin, or they just return a discrete bin value, so integer or string, and that is always the same for the axes, for an individual axis. They support a length, they support iteration, which gives you the obvious thing from those two things. And then they have a traits property, which has either has circular and discrete. So it has at least those two things. Okay. And then if you use it, it's statically verified by MyPy. So if you just say, hey, I take a plottable, one of these plottable histograms, then it will verify that you actually only use those things, the things I just showed you. If you want to write your own library, and so say like uproot or boost histogram or some new library, and you want to make it support this protocol, then this is what you would do at static type check time. You would get this, it's actually plottable histogram, not plottable protocol. You would just import like that, this. And then, oops, sorry, jumped. And then you could just you could say, well, only if you're type checking, or if this file could just be a type check file only, then just take some value, doesn't matter what it is, but it's going to be a plottable histogram. And then you can just cast your histogram, none to your histogram. So this wouldn't work at runtime, doesn't make any sense. This would just be none, but it doesn't matter that this is none, because what this is doing at type check time is it's checking. I have an instance of some sort of my histogram, and is it a plottable histogram? So that's what it does at type check time. So this will fail a type check if you didn't fill in all of the necessary bits and pieces. So this is how some of the other libraries are able to verify they really are plottable histograms. Okay, so let's take a look at this in action. So let's do a little plot of just some random numbers, and then we'll also try a little 2D demo. Okay, so I'm just going to set up some initial libraries here. I'm going to create a random number generator from NumPy 1.17 or so, whenever they switch to this method. And then I'm going to go ahead and create a histogram. I'm going to go ahead and make sure we import hist here as well. Yep. And then I'm going to go ahead and take a histogram, and I'm going to fill it. And just to be fast, I'm going to fill it in 4 threads. And then I'm going to hand this to MPLHEP. MPLHEP doesn't know anything about boost histograms or hists, but it knows how to plot a plottable histogram, and this is one. So this is a plot. You'll see the correct values down here. I can actually change this to hist. Probably spelling correctly. And it can plot that as well. A few of these libraries have some optional support for picking up names, but because Boost Histogram doesn't support named axes, it couldn't be added to the protocol. So, but some libraries can check and just add a name if they see it. So there we go. We were able to plot that. We can also pass these to histoprint. So if I pass this to histoprint, .print hist, again, doesn't know anything about this library, but it knows how to detect and plot a plottable histogram. And let's just try a two-dimensional demo of this. And you'll see a little bit of rebinning here. And since I switched to HIST, I can actually switch to the HIST binning and make that a whole lot easier to read because there's so many extra characters there, including parentheses. I don't like parentheses. Yes. Okay, and then that's the exact same thing, but this time you can now actually read exactly what I'm doing up here instead of having lots of extra characters. All right, and then we can try a two-dimensional demo. We'll just open this image and turn this into a NumPy array. And then again, grab a random set of random numbers. We're going to throw those. We're basically going to do a probability of whether they hit this image or not. So this is a way of turning this into a list of tracks, and these tracks are things that either hit or didn't hit this, and they tend to get deleted if they didn't get hit this using this probability. So we're going to go ahead and fill this. We've seen HIST now, so we can do this in HIST. And we can go ahead and switch this over so that we can get access to our names. Okay. Try to change too much there. There we go. So we can go ahead and import and fill that. And then I can go ahead and this is actually based on an older, actually, I'm going to do h.plot here. There we go. So there you see the plot. And you could manually plot this if you wanted to, but that's, I can go ahead and show that. And this is just building our own little plotting function out of raw matplotlib primitives. And you can even rebin this or zoom into a specific spot. And the nice thing here is you can actually just read these coordinates off these axes and just plug them in here and just stick J's on the end. So from X, it starts at 0.2. From Y, it starts at 0.8, or it ends at 0.68, sorry, on X. Then at Y, it looks like it starts around 0.5 and ends around 0.8. Again, and you just can read that off of the histogram up here, and then you can get the zoomed in version down here. So this is really great for making cuts and looking at things, balance analyses, various things like that, where you might want to look at a specific subset. You can also, of course, sum across this. So for example, do a vertical sum there, and then I'm using this weird plot thing that's only plotting 2D stuff. And then if you don't add star, you can take a look at what the profile would look like across. And again, I just take a look. Okay, so let's switch over to Aman, and then we'll have some tutorial materials to look at.
Hi, I hope I'm audible.
And do you want to share your screen, or do you want me to just keep sharing?
I'll just share my screen. So yeah, I hope the screen is visible. We're going to talk about the future plans of it and like the current features as Nino discussed, we've added. So what we have a lot of features currently coming up, which also integrate with the PyHEP and various other libraries. So let's get the overview. First, we'll be planning on introducing an interpolator. So it would be a class which could interpolate over histograms, and that has a statistical advantage. And it could take the histogram and return the interpolated values. and we can have various interfaces for the kind of interpolation we want. For example, we can have a hist dot inter. For example, if the class is dot inter, we can just run that, and we can call linear interpolator, and it would do a linear interpolation on the histogram that we have passed. And similarly, we could do that for cubic interpolation. So what the basic plan is that first we introduce the basic ones, the standard interpolations, and then we can also give support to the users to make their own based on different parameters. So it would help in better estimation and interpretation of the data. Then another feature that we want to add from the COFFIA library would be the plot grid feature. It would help in creating a grid of plots. And after that, we can also look into arbitrary rebinning. So the current issue with rebinning is that it requires a lot of preconditions to work on. So suppose we have arbitrary rebinning, and suppose we have a very large histogram, which are inherently difficult to work with. Almost all libraries, like very few libraries, support histograms with large bins. So if you have a lot of bins, what we can do is we can arbitrarily rebin it. Suppose we match the edges on upon a function, and then we have the new bins which can be plotted faster. So that basically improves the efficiency of the plot. And then we also plan fills from awkward arrays, as Jim presented yesterday. So we could take in awkward arrays, and the fill function would take it in intelligently, and then we can use the various features that are provided in awkward arrays, ak.flatten, ak.fields, and ak.unzip, to sort through the data, and depending on the different kinds of data, we can fill those. Another feature would be statistical functions. So we have functions in root and in other libraries which can be added to hist, and those could be used to handle efficiency histograms, and again it would help in statistical analysis. So it would compute the calculation of efficiencies and their uncertainties. That is another feature that we have planned. And other minor features would be improved reps. As Nino discussed, reps, we have the different representations of the histograms that we define in the Jupyter notebook itself. So if we have histograms with various axes and multiple information, we would like to cut through that information using certain commands. So when we have better details, and we can have configurable options which give us a better output. So suppose we want just a specific part of the rep, we can get that. And we're also planning to integrate the hist package library with fitters. So that would ensure that it interacts properly with various libraries and fitters such as zfit, PyHEP, and goofit. And another thing, we're dropping Python 3.6 support. So we made just a release was made just a few hours ago, and that was the last release with Python 3.6. And our development branch would soon drop 3.6, and then onwards we'll support 3.6, 3.7, and above. So that's what we've planned in hist. And now Henry would dive into what we've discussed, and we can get in the tutorial and see how to use histogramming features that we have discussed today. Thank you.
Okay, I'm just going to share this again. Okay. So hopefully at this point you're either running locally or you tried out the binder, so you'll have something to run. But let's take sort of a more in-depth look into some things that we can do. So the first one, we'll just sort of glance over this first tutorial. This was sort of a high-level introduction, and it was originally targeted at a bit broader audience, but it gives you a sort of very gentle introduction into histogramming, sort of assuming that you know NumPy, and then moving over to histograms. So let's just run a little bit of it. There's a couple of useful things of there. I'm not going to talk through all the details here. So that's why you might want a histogram. And then, as we've already sort of pointed out, histograms are sliceable. You can slice them by either their bin indices, or you can slice them by the data coordinates. This is often easier if you're reading something off. You'll see these things are the same. You'll also notice that they are carrying along flow. So they have flow bins, just like say a root histogram would. And you can rebin them really naturally. You can sum them up. I assume this audience does know why this is not the same number as the number of things we added. So I'll just do the answer here. So flow equals true, and that's actually the full number of bins. This is what it describes in here. So we'll not do that exercise. And then there are a variety of different properties. So you have an axis, basically something that looks like a tuple of axes, and then you can access centers, edges, widths, name, so various things like that. You can actually avoid this this 0, and you'll just get back a tuple item, and this will actually be correct for multiple dimensions. So I should be able to just broadcast this together and use it if it's something like a centers or edges or widths. So that's quite powerful. And then you have values, variances, and counts. Counts and values may often be the same if you're not dealing with a mean storage. And variances may return none if it can't track it. So if it's not weighted, this may return none if it doesn't think it can track what the variance actually is. Depends on how you feel. And we can actually get a raw view of the data as well, which is for a regular set of doubles. This is really simple, but for other storages, there's more to this. And there's, as you've sort of seen, there's multiple ways to define these. We have this sort of the standard method, and then there's also a shortcut method that hist adds. You can actually write this out now if you want. This was originally different so that to make sure that you wouldn't accidentally make a mistake and put this inside here. But actually you can do that now. Partially because now we have a new. So let's say if you made a mistake like that, it actually just still works. So that was the thing I was really worried about, that you would, these two things look similar, but now that works too. So you can use the full names if you don't like switching between the sort of the short names and the full names. This is nicer, and in fact, the tab completion will actually recommend this one now. It won't show you the other one, won't show you the short one. Okay, so that's just sort of a quick little overview of sort of the key bits of things that you'll need in order to play with anything. So this is an example with more dimensions. So let's try playing around with this histogram. You've seen how we did all the stuff in one dimension. Let's try playing around with this in 2 dimensions. So for example, if you want to just select out this piece, let's say a plot. Let's do h.plot. Now we get a little bit nicer units here. I'll just do that way. How would you look at just this piece? So try that for a minute. Use indexing expressions and try to select from -2 to 2, -2 to 2. So in this case, -2 to 2. in value space. This is just a one-line thing, so you should be able to just paste it into the Slido if you like, if anybody has an answer for that. And then I see we have questions, so I'll answer questions after that while people are playing with this a bit. So I'll answer some questions and give you a chance to just play around with indexing this. There's a few suggestions there. The next thing I would try is look at profile over in y-axis. X. There's several, actually a couple different ways to do that. And S, not X, W. Because I see the units, I see the little labels up here. So try this next, and then I'll answer questions, and we'll come back to this. So some questions. There we go. So I'll start with the most highly voted, since Slido puts the ones that people are voting for. So if there's a question you have as well, just vote for the existing question, and they will come up to the top and be more likely to be answered. So for accumulator storages, are wider statistics like Poisson or asymmetric errors going to be supported? So right now we have just a set of three special storages. We have a profile, a weighted profile, and then we have which is a mean, and we have the weighted sum. The issue with adding more of these is that if they require different calculations, you have to implement them in C++, which is really easy in Boost Histogram C++ side. But then you have to add them to the library, which again is not particularly hard, but then it will make it larger and slower to compile and have issues with running out of memory and things if you get too many of these. So some things, yes. What we'll probably be trying to do, sort of very long term, would be to add a way to adjust this by, say, having storages of different sizes and then passing in a C-types pointer. Because we currently do this for transforms. So the answer for transforms, if you have a different transform that you want to transform a regular axis into something else, you can write anything you want, write it in, say, in numba and C-types as a C callback, C-func, and then just pass it in and it works. And it gives you about 10%, gets you to within about 10% of the performance of the raw C++. So there might be some way to do something similar with a general storage backend, and that would be a very valuable addition. Okay, how well does Boost Histogram and HIST deal with computing stat errors in the bins? It should deal with those. You need to use a weighted histogram, but in that case, the statistics should be propagated through as when you're check dividing two histograms, but definitely most of the operations and fills and things would work there. I will verify. I think dividing two histograms works at some point. I think it had a bug originally. Will interpolation use bin centers or edges? I think that would have an option to customize it. There will be a general interpolator class that these things will be based on, and it'll have some structures. So it should be really easy to add your own interpolator when we'll provide some default ones like linear and stuff. So linear itself might not have an option in it. Depends on how easy that is, but it would be very easy to add interpolators that use either one. What is the best practice for converting PyRoot histograms? Something which can be plotted by matplotlib. Well, certainly you can just write, you can actually now just pass them in. So MPL-HEP uses UHI and the UHI library, as that provides really nice, handy ways to get some of these things. And the UHI library and its adapter actually supports PyRoot natively. It picks up, it detects if if it's being passed something that's PyRoot, and it will convert it to a simple object that happens to exactly conform to the plottable protocol. And so the easiest way is really just hand it to NPL-HEP, and that will should just work out of the box. And it's because of the UHI helper functions. Things that do not use UHI right now, you would then have to just manually do that. Though I would actually really like to add direct UHI support to PyRoot. I think they might be willing to accept that as a Pythonization. So that's something I've intended to do for a while. Is all the information in the original input histograms in the stack accessible from the stack? Yes, they act just a lot like, well, they are a container. So in fact, something that I didn't realize worked until after we released, and then I did, I think it was in here. I was adding a stack, what was I doing? I was adding the stack true and his type fill just to see if that worked. And I didn't like the way that this one came out with this on top. So I thought, well, why don't I just try reversing the stack and plotting it, and it worked. And that was actually a last minute change in stack to add the fact that and if you pass in a tuple here and change the stack around, it still returns a stack. But you can always pass a stack to the stack constructor. So you could just say star and then whatever collection of histograms or even star stack, because it's iterable, and make these any way you want. So yes, there it just use bracket 0, and that's the original histogram. And it actually has a title as well, if it came from the .stack constructor, which I assume is how most people will do it. I assume most people would probably create this axis beforehand, fill it, so then you get the performance benefit when you're filling, because you're only looping through this once. And then when you do this, the name for each one of these things, so good and bad, actually gets attached to the items in the stack. So if I do, I have to run all above selected cell. Okay, and then if I run this, and so if you take a look at this S, so that's the stack. If I just index in, those are the original histograms. I can even slice, and I get back a stack, which was the thing that caused that other trick to work. And if you look at one of these histograms, these actually have a name attribute that's been added, and that's the original cell value that it came from. If I were to do a stack over something that was not strings, I would get an integer or a pair of floats here, which is a little bit weird for a name, but it's still extremely useful for filling in labels and such. We're down to 1 vote question. So if anybody wants some of these, I would then either add some votes. I say add some votes, or we'll answer those later on Slack. Almost said stack. Okay, so let's go back to this example. So of course, the answer for plotting, the answer for plotting was simply just h minus 2i to 2 j, sorry, to 2j, and that's how you would that one, except I have to do both because it's a 2D histogram first. 2j, and then dot plot just to see it. It's because I like this plot better. Honestly, this one's not too bad. It's not that many bins. And then for this example, there were 2 ways to do it. One would be to, if you want a profile. So what I asked was I wanted to integrate over the W axis and just look at the S axis. So there's 2 or 3 ways to do that. One would be to just use indexing expressions. So I could do some, well, I don't have to put the colons. I could do that. And that would give me just the s-axis, what you see, because it's passing these names through. This is very helpful. And then it's summing over the other axis. This, of course, is available using names as well. So if you're using names, you just pass a dictionary in here. Oops, dictionary in here, and this allows you to apply a single value on each. So I could do 1 colon. That would be the same thing, or I could use, as I promised, the name, which is no, I want to sum over W. Sorry. Actually, I need to check and see what the name is. Capital W. So capital W. W. There we go. And I could use the profile. So you can say h dot profile. I can again give the integer or the name. Pretty much everywhere you can give the integer or the name. So I can give it profile out s, that will give me W, and I can profile out W, and that will give me s. So it behaves a lot like this thing. If you have multiple dimensions, you always give it the dimension you want to remove to make the, not profile, I don't know what I'm doing. Sorry. Profile will give you an actual profile histogram. So these are means across this, which is really nice. But what I actually wanted to do was project. And then I project the s-axis out, and that gives me s. There we go. That's what I was expecting. So you can project as many as you want here, and it will do that in this order. This is actually a good way to swap the axes as well, because you can't do that in UHI, but in indexing UHI. But you can do that with project. Okay, let's just do one. Let's pick another example to do. Oops. 3D histogram. All right, let's take a look at the density. So you can just call dot density, and that will get a density. Currently, just a direct array, but that's a quick way to get the density. You could actually compute that yourself really easily as well. Those are some UHI examples. Let me check the questions again. All right, we have a few that are multiple voted, so let's answer those. So about well, I think the statistics improvements will help there for the support for non-standard errors, but I'll get back. I'll get back on that one. I think we should be able to do anything root can do. So we'll just keep track of the x values for accurate interpolation. If you use the right type of histogram beforehand, yes. And any plans for a stack protocol in that? Possibly. I've thought about that. Since we now have a stack object, we might add a stack protocol as well. That would be nice for these things. Right now, it's really just a list of plottable histograms. So that's the sort of the current protocol, but it would be nice to formalize that. All right. Any more questions? Okay. Okay, let's just look at one more example. So we saw some plotting. Let's take a look at the different types of storage. So okay, so here's some different storages. So we can pass in an integer. storage. So this is an integer storage choice. There's 7 different storage choices, and that produces actual integers from these things instead of the doubles you saw before. It's not particularly faster than doubles, and doubles cover pretty much anything you would want to do, and you can scale and stuff doubles a little bit more nicely and fill with weights, but you can do actual integers if you'd like. There's a double storage, which is the sort of the default. And you can, and the double, this thing that you end with is actually the storage name when you do the quick constructor. So let's take a look at a weighted storage. So I'm just going to try switching this to dot plot.
You already flushed it? So you flushed it already?
And
Well, you don't need to flush now. It's fine.
let's fill this with a weight. So weight equals 2. So you'll notice the plot of errors went away because it can't track these through this anymore. If I switch this to a double storage, it still can't track through that. And but if I switch to a weighted storage, it can. So this will store extra information to track these errors. And now it can go through this transformation because it's storing more inside the histogram. All right. I think that's you could also do mean storages here, which will then take a sample and it will do basically the same thing as a T profile. Okay, let's go ahead and end with this final question because then our time will be out. What does underflow, overflow, and flow represent here refer to? So similar to root, by default, boost histogram and hist keep track of anything that misses above and below. Actually, we pointed that out, I think, in this one. We just kind of breezed over it. But it's actually, even though when I filled this, I definitely, I should actually fill this one. Some of these actually do fall outside this range, especially right here. You see there's definitely some things in the overflow bin. So if I look at this H dot, well, it's hist overflow, you'll see that there are actually some entries in this overflow bin. Right, let's see if there's any in the underflow bin. There's a few in the underflow bin as well. So it keeps track of those, and that keeps track of all of these. And if you're integrating over, so if you're doing a 2-dimensional histogram, and then you're summing over everything, it will include those flow bins. So you'll get exactly the same histogram out that you would have gotten if you had just originally made a histogram over that 1 dimension. So there's no harm in adding extra dimensions when you have flow bins. You can put explicit endpoints to turn off those flow bins if you do want to actually integrate over a fixed range. All right, I think that's all we have time for. So there's lots of extra examples here to feel free to look through. And we'll try to answer any of the remaining questions on Slack.
Okay, thanks very much, Henry. It was a perfect time and super interesting. So thanks to all of you for that really great tutorial. And we'll now move on to Kyle Krenmer, who's going to be presenting on MadMiner.
Hi, good morning. Can you hear me okay?
Indeed, we can.
Okay, great. Then I will share my screen here. Actually, my video is kind of sharing the screen already, I suppose. Should I just can you see my mouse and the web page here?
For me, it's a little low quality in terms of the resolution, but that might just be me.
Okay, well, I can also, instead of using the video part, I can just I was using OBS to try to so that you can see me as well. But
Oh,
maybe that's not worth. Yeah, I'll just stop that and share my screen. Okay, hopefully that looks a little better.
Yes, much better. Thank you.
Okay, great. Okay, well, thank you very much for having me. I'm going to be talking about MadMiner, which is a Python-based tool for what's called simulation-based inference and high-energy physics. There are several links here. So there's links to the documentation for the tool, where it is in GitHub. There's a Jupyter book, which I'd like to point to. And then I have a couple links to specific things within the book. So there's a part about running MadMiner on a workflow execution system called Rihanna, which is important when you want to sort of scale these up beyond running on your laptop and run with some sort of a larger parallel computing backend. And then there's a little binderized morphing demo, which is maybe fun to play with, and one of the sort of few things that there will really be time to actually interact with, I think, given the amount of time. There's a link to I've given a couple of tutorials on MadMiner. They're usually more like an hour long. And so there's a recorded version of that video that goes through kind of an entire workflow. And then I have some slides. And so if it's okay, I'm going to start with the slides just to try to frame things. And then I will come back to the Jupyter book and we'll have a little bit of time. Okay, so let me switch to the slides. Okay, so this is like I said, the topic is about this tool that we've developed called MadMiner over a few years, and I'd like to acknowledge all the people involved. So there was both a lot of methodological development in terms of machine learning and statistics, and then followed by tool development. So Johan Brimmer was the primary author of MadMiner, the tool, and also one of the major contributors on the methodological side. Also on the methodological side was myself, Gilles Luc, Juan Pavez, Marcus Stoye, and Felix Kling. And then Arena and Sinclair came in to help out a lot in terms of sort of dockerizing all the different parts and helping build workflows and integrate this tool into this Rihanna workflow execution system, which I'll describe. Matthew Fikert has helped a lot in terms of sort of getting the Jupyter book there and helping us clean up our Docker files and various things like that. And then Tillman Plain, Sally Dawson, and Sam Homler are phenomenologists that have used this tool to do various types of studies, and I'll show one example plot. The work has been sort of extended over a few years and has been supported partially by the Moore Sloan data science environment, and then some NSF projects like DianaHEP, which then grew into IrisHEP, and another project called Scale. Okay, so this is just a preview of the Jupyter book. There's the link to it at the top, and I will come back to this as soon as possible. And again, I'd like to thank Marina, Sinclair, and Matthew for helping get this into nice shape. I mentioned before that there are some video tutorials. So there's like about an hour-long tutorial which is running MadMiner locally on your computer using Docker. And then there's like a 30-minute tutorial where it's basically the same thing, but it's running remotely on a Rihanna cluster. And if you don't know about Rihanna, this is a tool that was originally developed by our group to support a backend for something called a recast, which is like a reinterpretation system. And then we sort of pulled out the workflow execution system, and CERN took over development. And so it's its own product now, branded as Rihanna. And that runs on like Kubernetes type platforms, and also HPC and larger like grid sites and things like that. And it takes advantage of like Docker and Singularity and workflow languages like Yadage and the common workflow language. So that's kind of like a big overview. So the difficult thing here is that most of the notebooks that I have, when you run them, they either they're fairly computationally heavy. So unfortunately, like Henry's tutorial was fantastic with this very fast turnaround on histogramming. And here we have to like generate a lot of data or train a machine learning model, and that just will, those steps might take a little while. So so it's not as easy to have that kind of interactive experience. So so I'm going to give a few slides about just like what it's all about, and then I will scroll through the Jupyter books a bit and give you a feel for what how the tool is used and things like that. Okay, so let me get on with motivation. So the basic idea of what this tool is trying to do for you is that we have very high dimensional event data at the, say at the Large Hadron Collider. And what we would like to do is put constraints on, like limits or confidence intervals on parameters of some new physics theory. And this tool, it can be used in different contexts, but it really shines when you talk about trying to do limits on what's called effective field theory. And so in effective field theory, you have like the standard model, and then you add some additional interactions. And that what's going to happen is instead of like making a new particle where you see a big bump in the data or something, what you're talking about are small deviations to the distributions that you would expect in the standard model. And so you can kind of generically parameterize that with an effective field theory. And basically then your goal is to measure these coefficients, which in the standard model, all of these would be 0. So if you look at this plot, 0, 0 is like, this is like what you would expect. Oh, this is a different scaling. Okay, whatever. Usually, in my parameterization here, 0, 0 is a standard model. But you would be looking for, trying to make measurements around the standard. Okay. So the way that this is going to be done is it's sort of you're trying to do statistical inference. So you need to make a likelihood, and there have been talks earlier like ZFIT and PyHEP and cabinetry, et cetera, that talk about a lot of how to build a likelihood and how to do statistical fits. And so this is similar to that. Here, this is like, the formula for our likelihood function, where X is the data and theta are the parameters of the likelihood we want to fit. And it looks like sigma here is like a total cross section, which depends on the parameters of your theory. And this is the differential cross section. And the idea here is that we want the X, the data, to be high dimensional. So most of the examples that we've seen, the fits are usually done in like, one-dimensional histograms or maybe two-dimensional or something like that. And here we would like to be able to work with, high-dimensional data, and that's going to be the challenge, is how do we, build this likelihood function. Okay, so the bad news here is that for our particle physics processes that we're working with, when we work in the high-dimensional data, we don't have a tractable likelihood function. There's no like function that you can call that's like, this is the likelihood of this complicated LHC event. And why is that? So if you think about the way that we simulate things, we start off with some theory parameters. We have tools like MadGraph that deal with like the hard scattering, where there's like Feynman diagrams and things. And this is where the new physics is going to modify the interactions. And that gives us like parton level momenta. And then we take that parton level momenta and we feed, and we feed it into the next part of the tooling, which does the parton shower. And that gives you lots of like quarks and gluons and things. And then finally, you have hadronization. And then you take those particles and you pass it to something like Jayant or maybe a fast simulation like Delphis. And then you finally get the detector level data, and then you usually reconstruct it. And so the quantities that you're observing, have gone through this long simulation chain before you get to whatever like jets and electrons and things that you're working with. And so again, you have this big tool stack. So MadMiner is going to somehow need to leverage all the existing tools that are sitting around in our simulation chain. Okay. Now, if you think about what we call these Monte Carlo events, right? And what Monte Carlo sampling you can think of as an integral. And so what this Monte Carlo, the series of simulation tools are doing, when they have all the random numbers inside, is they're sampling from this very big probability distribution. And they're basically trying to do this integral over all the things that could happen in the detector, all the things that could happen in the shower, and all the parton level kinematics. And you can't literally do that integral. It's in like 100 million dimensional integral. So you can't actually evaluate the likelihood function. So what we usually do is we simulate a bunch of events, and then we pick particular observables that we think are going to be useful, and we fill one-dimensional histograms of those, and we do that for different parameter values. So these one-dimensional histograms you would call like summary statistics or something if you're a statistician. And so we need to build like a, some model for that, and then we would fit that. So the high-level picture is parameters go into a simulator, you get simulated observables, you calculate some summary statistics like invariant mass of 2 particles or something. Then you do density estimation, say with histograms. That gives you some approximation of the likelihood function. Then you take real data, calculate the same observed summary statistics, put everything together, do inference, and then you get out like confidence intervals or limits or p-values or whatever you want. So that's the high-level picture of what we normally do. And that's where tools like PyHEP and ZFit and cabinetry and et cetera come in. Now, this has been great. This is how we do things. The problem with this for, say, for effective field theory is that when you compress onto these like one-dimensional summary statistics, you usually lose quite a bit of information. And unfortunately, you can't scale this up to high dimensions because you can't really effectively fill a histogram in like 10 dimensions because you would need an extraordinarily large amount of simulated data. Okay, so what we would like to be able to do is sort of work with high dimensional data, include the state of the art of like all of our simulation tools, like all the QCD stuff that's going in MagGraph and Pythia and Sherpa, et cetera. And then get out some sort of approximation for the likelihood, just like a histogram that we can evaluate very quickly, like in microseconds, and then do fits. So this is the high-level picture. Basically, we're going to take the parameters that we want to measure. We're going to stick it into the simulation chain. It's going to produce us some synthetic observed data. We're going to train a neural network that's going to depend on both the data and the parameters we would like to test. That neural network is going to try to approximate the likelihood ratio. So we need to train the network with some appropriate loss function so that the network that, once it's trained is approximating the likelihood ratio. And once we have that likelihood ratio, then we can stick it into some statistical inference thing and do fits on our EFT coefficients. So MadMiner is doing all of this, okay? And that's why it uses lots of other tools along the way. Like it uses our typical simulation tools. It uses, for instance, PyTorch for the neural network stuff. But it's encompassing a lot. And so there's also a lot of software dependencies. That's where like Docker is very important. So I hope you can forgive me that why I'm giving you this kind of overview slides instead of just jumping straight into it. The other thing that MadMiner does, and this is where it gets its name, is that instead of just running the simulation chain and getting out observed data and training a neural network, which is what probably most people that have used machine learning and at the LHC are familiar with doing, here it's a little bit unusual because the neural network doesn't just depend on the data, it also depends on the parameters you're testing. So this is the so-called parameterized neural network. But in addition, MadMiner has this ability to pull out some additional information out of the simulation, which we call this process mining gold. That's where it gets its name. And so this augmented data, which is richer than the normal simulated events, we can use that together with some special loss functions to try to learn the likelihood ratio much more efficiently. So this is not so trivial to do, this mining, this augmented data from the simulator. And so that's the other thing that MadMiner does for you that's valuable. So I'll just say a word about that. Okay, so as before, this is like the simulation chain is sort of calculating this big integral, conceptually at least. Now the only dependence on the parameters that we want to measure is over here at the parton level. And so if you look at, for instance, this likelihood ratio, where you imagine a full, like one event that's gone through the entire simulation chain, all the parton shower and Jaeon and everything, you freeze all of that information, and then you ask how much more or less likely would this particular simulated event have been under two different values of the parameter theta. And if you do that, the part that comes from Jaeon cancels, the part that comes from the detector and the showering cancel, and the only part that you're left over with is the ratio of the matrix elements. And so this quantity is actually something that's tractable and you can calculate. And so you can pull it essentially out of the integral, and that this we call the joint likelihood ratio is one of the types of augmented data that we can pull out of the simulation chain. But to do that, we need to be able to still access the parton level kinematics and to be able to evaluate the matrix element under different values of the, like for instance, the EFT parameters. And so once you do that, I'm not going to go through this, but basically this is the information we can calculate. This is the thing that we want to, this is the target that we would like to learn. And so, and basically conceptually, the idea is the red curve is what we would like to learn. And this data that we pulled out are like the blue and green dots. And so it's going to make the machine learning problem much easier, and so you're going to need much less data to learn. And so here's like, technicalities about the loss function and the math that shows you that if you minimize this loss function, you get the thing that you want. For this audience, I won't bother with that. And then there's a similar thing, another type of augmented data, which is similar. What basically you take the derivative of the log likelihood at that point. And so this, being able to take that derivative is, you would imagine may be difficult. Like you might imagine you have to simulate the whole chain with one value of the parameters and then change the values of the parameters and simulate again and somehow try to take, finite differences to approximate a derivative. But because of but there are some tricks that you can do, which I won't bother spending much more time on, that have to do with how the differential cross-section depends on the parameters, which allows us to take this derivative exactly. And if you wanted to work through that, it's kind of a pain. And so MadMiner takes care of basically calculating this derivative for you, and then adding that as augmented data to your data set that you're going to train your neural network thing. And we also have the appropriate loss functions so that when you do that, once you do the machine learning stuff, you get out this quantity that you want, okay? And this quantity, for those that follow this kind of stuff, is closely related to, it's like the generalization of what's called optimal observables. And so they're, from the name, you can tell they're going to be like powerful things for trying to make measurements at the LHC. So MadMiner basically automates all of this, okay? And so there's the high level picture of what's going on, of what MadMiner is doing for you. And at this point, maybe I'll jump to the notebook. I'll just say that here there's lots of resources. There is the actual GitHub repository. There are papers there are papers that have the methodology, and there's a paper specifically about the tool, okay, which is this one right here that works through a full realistic example with like TT bar Higgs, Higgs to 2 photons. It includes systematic uncertainties and all sorts of stuff, and irreducible backgrounds. It's a complicated example that we work through, and it has a reproducible notebook associated to it. There's it's on PyPy, and there's documentation. And so then the one thing that I'll show is just this quick example, which is that if you compare to the simplified template cross-section approach, this is a study that was done by Johan, Sally, Sam, Felix, and Tillman. But you get exclusion contours that look like the red dotted thing, and you want these contours to be as small as possible. And if you use MadMiner, you move from there to this small blue ellipse. So that's like a many factors of data, improvement in terms of sensitivity. So it can lead to a really substantial improvement in sensitivity for these like flagship measurements at the LHC. Okay, so I mentioned there's tutorials in this notebook, and so now I'll switch to the notebook. And I realize I only have about 5 minutes left to talk, and then a few minutes for questions. Okay, so if you click on the on the Jupyter book here, it will take you to this link. I'll make the text a little bit bigger for you. So again, you have this kind of overview. If you look about what do I want to say? Here's where there's a link to this demo video. There's some preliminaries here. The point is that this tool has a lot of software dependencies, and so they can be roughly broken up into the part where you're generating a bunch of training data, where you have dependencies on the simulation tools like MagGraph, Pythia, and we ship with a version that supports Delphis, because this tool can't interface itself directly to like the Atlas and CMS detector simulation, but you can still use this tool if you basically plug in the Atlas and CMS detector simulation. It's possible. But we have basically some Docker containers that bundle all of the dependencies for the simulation part. And then we have another Docker container that bundles all the dependencies for the machine learning part. And then there's the MadMiner tool itself, which is in both. Okay. So then, right. So in this tutorial, you can install Docker, on your desktop or your laptop, whatever. And then, so this is the first part is just about setting up Docker to make sure that you're set up with that. Then there's this is the kind of overview. Let me make this a little bit bigger, so you can see. So the very first stages are about event generation. And so when you do that, MadGraph and Pythia are going to be the tools that really do the event generation, and they're writing data out in the common formats like the LaSouche event file, and then the HEPMC files and things like that. MadGraph is going to take care, MadMiner is going to take care of sort of steering this, because there's a lot of configuration that has to be done that has to be consistent throughout this entire process. And so MadMiner will basically keep track of some configuration information that gets reused at the various stages. And that is going to be written over here on the right into an H5 file that MadMiner keeps, that has some at first just some very lightweight configuration, and later it's going to keep track of the actual training data and things like that. Okay, so you run MadMiner, you generate a bunch of events, then you can run through Delphis, right? If you're wanting to do a fast simulation sort of pheno analysis. You can also here we can, if there are questions, I can talk about what would happen with actual experiments. But here, that you at some point you need to simulate the events, and so we package up an example with Delphis, and also like a simple smearing function that's fast. So that will output root files, and then we can read in these root files and basically reformat it into an H5 file, and then which is going to be kind of more appropriate later for the machine learning portions. Then there's a piece where once you've simulated simulated some events, the problem is when you simulate events, you're only going to simulate them with a few specific values of the parameters that you're testing. Like you might generate a large standard model sample, and you might generate a few other samples with different values of the coefficients for this effective field theory. But in the end, we want to set limits in this entire continuous 2D space. And so the sample augmenter allows you to do some tricks where you basically can then continuously interpolate exactly to any different value of these parameters. And so to do that, you have to calculate some things and store that information, and that's what the sample augmenter is doing. So it adds that to these files. Then you get into the machine learning portions where you either learn a likelihood ratio or this score, which is like the optimal observables. And then you get into the kind of statistical inference piece, okay? And so I realize I'm running out of time now. So these different parts of the tutorial deal with all of that. So so first thing we can see like the configuration for, here's like the tutorial that's going to, sorry, I should start here. When you first want to define the process that you want to study, here's where you can actually talk to, this is sort of, referring to blocks of MadGraph parameter cards. So it's going to be able to sort of write the parameter cards for you and do the appropriate things. There's this morphing tool, which is what allows you to do this interpolation exactly. And so to do that, I don't really have time to go through all the things, but you need to run at some number of basis points. And so that's what's happening here. Later, there's actually running the simulation to actually generate some some observed events, and down at the bottom of this, sorry, all the printouts and things, you'll actually see plots of simulated events. Then there's training the likelihood ratio. So this is where PyTorch gets involved in the machine learning components. Okay, and then you finally get to limits on the actual EFT parameters. So you can see, we can do a comparison to a histogram-based approach and this machine learning-based approach. So you see, examples here. So then with the last little bit that I'll say, this notebook has interactive buttons so you can launch in Binder. If I go to one of these that it has restarted, is it? Well, I would have to restart it, but it basically, that example is this interactive morphing demo. And if you click on it, basically these black dots are where you actually simulate events. These are the so-called basis points. And the color is basically the interpolation to all other points in the parameter space. And this is a kind of, optimizing this basis is an important thing. And so that's, we have whatever, this is just fun to play with basically. And then the last thing I'll say is that when you want to actually run this at scale, you don't want to run this on your laptop because you need to generate a lot of events. And so that's where we use Rihanna and Yadage, which is a workflow language, and MLflow and various things like that. And you can run this on Rihanna. And so it builds this workflow, which basically parallelizes this, that you can see here, many different Pythia jobs running, many different Delphis jobs running, combining into one big training data set, and then running the machine learning with different configurations, evaluating them, and then final plotting and things. So we have the workflow there, and you can deploy that onto Rihanna. So I will stop there. Sorry, I went a little bit longer than I wanted, but we have a few more minutes for questions. I hope that's okay, and thank you very much. So let's see.
Thanks, Scott. That's great. If I sent you on Slack the link to Slido, so if you just want to go through the top questions there, then we can in the 3 or 4 minutes we have remaining, that'd be great.
Yeah. So the first question is how to prevent the neural network from picking up unknown mismodeling as signal. Yeah. So that is a great question. That kind of applies to all machine learning style analysis. And so while it's important, I think maybe from, I think it's a little bit factorized maybe from the focus. So maybe we can follow up on that on the side. It's not that I'm trying to avoid it, but it's in terms of like, PyHEP, maybe it's kind of, so you do need to worry about it. MadMiner does support dealing with systematic uncertainties and things. So you can start to do like all of the typical things we do with systematic uncertainties. But of course, it's an important question. The next question is how experiment specific is MadMiner? So MadMiner is not at all specific to an experiment. So you stick in the detector simulation at some point, right? And you can put in whatever detector simulation you want. And so if you, for instance, use Delphis, you can use, Atlas or CMS. You could, in principle, stick in LHCb or something. In terms of like what is it at the LHC, it's using MadGraph, right? So you could change to an E plus E minus collider or a mu plus mu minus collider. You could change the center of mass energy. You could have polarized beams. So this tool is excellent, for instance, for doing studies like we do at SNOMAS about like what is the potential reach of some future collider. You could change it to a different collider, stick in a different, fast simulation of Delphis, and say this is the sensitivity of some experiment. So there's a question of will we be able to convince physics coordination in our experiments that this is reliable? That's another really good question. So within Atlas, there are the first studies that are using this in kind of a limited context. I will say that this is I would take the long view about this. Like I think in my mind, this is the long-term view of how we will do the EFT measurements at the LHC, and it will take time before people are comfortable. But there are several results that are coming out from the experiment, both Atlas and CMS now, that use parameterized classifiers. So that's one step. The next step is to use it in this EFT context. There, a lot of the work has been on effective field theory, but I think as I showed, you gain quite a bit of sensitivity. There are other groups now that are kind of repeating this and seeing that. You have groups like Sally Dawson. She wrote the Higgs Hunter's Guide. She's a pretty serious phenomenologist that's been using this to show like how much more we could gain. And for instance, this has been invited to give a plenary talk at Higgs 2020. So I hope that we're moving in that direction, but it's certainly going to take some time for the field to get there, right? Is it possible to include other Monte Carlo generators? That's a great question. Conceptually, absolutely. There's nothing special about MadGraph or Pythia or anything like that from the point of view of the methodology. In terms of the tool, we are connected to MadGraph because this mining gold, this augmented data that we calculate, we need certain things from a Monte Carlo generator, and MadGraph provides that functionality. So when we were doing this at first, it wasn't really clear that Sherpa, for instance, provided that functionality in a convenient way. And it's really at the hard scattering level, so all the generators should kind of agree there. But we are not tied to, for instance, using Pythia. Like if you wanted to do a different hydrogenization, you can, through the Les Houchemin generator, you can do that. So I would say the tool currently is tied to MadGraph and things like that, but conceptually it can all be extended.
Okay.
What is the
we should probably all the questions we'll make sure to put onto the PyHEP Slack so that people can follow up if they have additional ones. We should probably move on now, but Kyle, thanks very much. That was a great talk. And yeah, so we're now going to move on to Benjamin Zeitlin, who's going to be talking to us about rapids and hardware accelerated data science.
Let's see. Okay, can folks hear me?
Yeah, we can indeed hear you.
Okay, great. Yeah, so my name's Benjamin Zeitlin. I'm a software manager at NVIDIA, and I'm going to talk about GPU data science, which sounds like a crazy thing to do. But first, let's maybe take like a condensed historical look at what data processing has been like for the last like 10 or 15 years. So since the introduction of Hadoop, we had this workflow that was pulling off this distributed file system called HDFS. We query some data. We have to write temporary storage back to HDFS. We have to read back in. We do some ETL on those things. We write back to HDFS, and then we finally read all that data back out. And as we go down from the lines from Hadoop to Spark, we're getting rid of these gray blocks, the HDFS reads and writes. Like the major advancement, or one of the major advancements in Spark when it was first introduced is that it could do way more in-memory processing, whereas Hadoop could not. So we get a major improvement. We also got the community around data processing and analytics was thinking more about how to bring in a larger community into the space of data processing. So we go from Hadoop, that's written entirely in Java. Of course, there are other tools like Hive SQL and other people that are trying to layer on top of these things. But we bring in more developers by reducing language complexity or inviting more people to the table. Still, though, there is an appetite to go, how do we get the next 10x after that? And people started experimenting with GPUs with Spark or GPUs with Hadoop. But in this world of data analytics where you would pull data off of HDFS, then you have to, unfortunately, move data from the CPU onto GPU memory, do some kind of GPU processing. And because GPUs are resource constrained, they don't have as much memory as traditional RAM, you have to write that data back out to the CPU. And you get back into that same cycle that you see at the very top where we're pulling from HDFS, then we do reads and writes back from GPU to CPU. And we need to get rid of those things to actually get significant speedups in our workflows. And Rapids seeks to do that. So we have this initial read that comes off of HDFS, and then we need to make the entire workflow exist on the GPU. So not just a fast CSV reader or fast HDFS read, not just a fast matrix multiply, but the entire pipeline has to exist on the GPU and reduce the amount of reading or spilling that we invariably have to incur when we write from GPU to CPU because of memory constraints. So Rapids and friends, CuPy is not developed by NVIDIA, but Rapids' approach to the PyData stack has been to accelerate individually and well accepted PyData tools on the GPU. So for NumPy, a group at Preferred Networks built CuPy. For Pandas, Rapids built cuDF, and for scikit-learn, we built cuML. So each one of these libraries is largely single GPU there are some primitives to do multi-GPU things here, but we can, for this talk, let's think of these things as just a single GPU. So we can have accelerated pandas, accelerated machine learning models, or classifiers, and accelerated NumPy operations. And because we have those tools, we can then leverage other engines like Spark, or in this case, Dask, since we're at the PyHEP conference. I'll mostly be focused on Dask. So we can take those tools and accelerate the entire stack. So this is the Rapids kind of view of the world that we can take. We have QDF, QML, we can do graph analytics. Of course, we can interact with other deep learning frameworks like PyTorch, but we also care about visualization. Again, we really want to stay on the GPU in order to get that performance up. More recently, we've been expanding beyond just those kind of the building blocks of the PyData community. Specifically, we've added QSIM, which is a scikit image compliant API that is GPU accelerated, and QSignal, which uses the SciPy signal API. So really, we're just, for lack of a better term, like thieves within PyData. We take these APIs that become like NumPy and Pandas becomes the API definition, and then we use that to build our own libraries. And the contract here is that with minimal code change and in API compliance, you should get not just 2 or 2.5x, but 40x or 50x performance gains across an entire workflow. So far, we've been pretty successful. This started off kind of as a grand experiment. We had to reject a lot of assumptions that we had. But over time, we've seen kind of explosive growth. We started in late 2018. And in 2021, we're getting very nice downloads or usage of Rapids. I should also mention that unlike in the past, we're getting to the GPU, or at least in my experience, getting to the GPU is really hard, not just computationally, but also individually. Writing CUDA kernels is extremely challenging. Getting domain experts to learn CUDA to accelerate any of their workflows, be it in biology or in high energy physics, is a hard ask. NVIDIA has now decided to invest the resources to build out these libraries ourselves, invite other contributors from the community to help. But there is no longer, or there should no longer be that pain of getting to the GPU because you don't know CUDA. That we're trying to leverage the community and spend the resources ourselves in order to build these libraries. So in this talk, while Rapids has a very expansive portfolio of libraries, we're mostly going to be focused on Dask, QDF, and QML. So within Rapids, many of the libraries have the following stack, where we have an underlying layer of C++ and CUDA. We leverage common GPU or CUDA libraries like Thrust and Cub. We then add a Python layer to give us Python hooks. So there is a well-established libqdf C++ library that some users actually will use directly. People that, in my experience, mostly those users are in HPC, though there are some business cases where C++ is the desired language to use. However, we think that in order to get wide adoption of GPU usage for data analytics, we needed to provide a Python interface. Though there's nothing that really prevents us from adding other languages other than resourcing and interest. So again, QDF provides a familiar Pandas-like API. We don't cover the entire API because Pandas is extremely large. We've also made some judicious choices where some of the defaults in Pandas will inhibit performance. So things like group by aggregations will, I believe in Pandas, like they come back sorted, and on a GPU, these aggregations are non-deterministic, so sorting actually prevents us from getting more performance. So we make some small changes here, but it should be extremely familiar to anybody who knows pandas. Again, some obligatory benchmarks. What we see when we compare pandas to a single GPU, so this is a V100, which is actually a slightly older GPU, to a fairly high-powered CPU, we get sort of off the charts performance benchmarks. I want to keep reminding folks that it's not about, we're not trying to create the fastest merge or the fastest sort, although in aggregate, we're trying to create a significantly faster workflow. So while we have merges that are 500 times faster, or faster sorts or faster group bys, what you should be asking yourself is how fast is the end-to-end workflow? Because if your problem is do all of your work on the CPU and then just do a very fast sort, that might work for some business cases, but it doesn't work for the far majority of users who aren't bound by a single group hive, but that are bound by the pipeline, which involves I/O, specific querying, a lot of ETL and ML, and some viz. I really like this slide because this is where I get to talk about how rejecting assumptions. We tend to think of GPUs as being just good at dense linear algebra, neural networks, drawing lots of triangles. Those are what we think of as what GPUs are used for. And when Rapids first started, it started off as kind of research, as an experiment. And that meant rejecting some assumptions that we had about GPUs, which going into this, most people will say GPUs are terrible at strings. And it turns out that they're not actually terrible at strings. It's not the wheelhouse of what GPUs are good at, but it turns out that they're quite performant. And there's things that we can even do to push on GPUs to make them even better. Because strings actually show up everywhere, we needed to confirm this, and we needed to actually push on things, push on string performance being as fast as possible. It is rare the case that when you get into analytics that you will just have numerical data. ETL kind of is always present, whether you're doing business use cases or image processing or even high energy. Strings kind of find their way into any workflow. On the ML side, we see something that looks a lot like cuDF. So cuML is, again, a library that maps to the scikit-learn API. The structure of it, again, is underlying CUDA libraries where we can call out to cuRAND, cuBLAS, cuSolver. All these libraries have existed for a long time. It's just not wrapped up in a nice package for PyData users to go out and consume. From those things, we can now build out cuML algorithms, linear regression, random forest, and we can add Cython to give us Python hooks. So we can use in the Python ecosystem. Just like with cuDF, we get very good performance, although varied performance depending on the algorithm. Not every algorithm will scale as efficiently on 1,000 threads that GPUs have to offer, but we still get very, very good performance across a wide variety of algorithms. So right now, I believe we have 26, at least the slide tells me 26 GPU algorithms or GPU accelerated algorithms, but we're always looking to increase this. So if you have, we're very responsive to community feedback. If you have algorithms that are not supported that you need for your workflow, please come to our Slack channel, which I'll post at the end, or even on GitHub. All of this work, again, is open source. We work in the open, trying to engage the community as much as possible. The nice thing also about cuML is that it's trying to GPU accelerate the classifiers. So we can still leverage the other machinery inside of scikit-learn. We're not trying to build a hyperparameter optimization engine, but scikit-learn already has that. And because our objects speak and look and feel like scikit-learn objects, or the classifiers at least, we can leverage the rest of the machinery within that library. So, as I said before, we can generally think of these tools as single GPU. So we need other tools to scale out that performance. So on the left, we have how we can scale up and accelerate things. And as we move to the right is how we can scale out and parallelize things. So Rapids can leverage tools like Dask or Spark or Blazing SQL, which provides a SQL engine on top of Rapids. And we can also leverage, although it's not listed in the slide, accelerated networking devices like NVLink or UCX. Those devices, UCX can use. There's a lot of. Let me back up because there's a lot of kind of meat in that. When you scale out, very quickly the bottleneck of your problem becomes networking. As such, people want to accelerate networking just like they want to accelerate computing. For GPUs on a single node, you can pass data back and forth with something called NVLink. Between nodes, many accelerators or many people turn to a device that's built by Mellanox called or a networking protocol called InfiniBand, which lets you do RDMA or GPU RDMA, and generally has higher throughput compared to regular Ethernet. Dask and Spark can leverage those kinds of accelerated networking devices. So what is Dask? Dask is a Python library for parallel computing. Dask comes from the idea that we have this very large PyData stack, and many people were at the time this was built 6 or 7 years ago, I think. We had this very well-known stack that I've said actually many times now already: NumPy, Pandas, scikit-learn. How do I make this go even faster? I have this on my desktop. I have a laptop, and underneath I have a desktop. Both have multiple cores. How do I make multi-core, multi-threaded NumPy or Pandas or scikit-learn or the next PyData library? There have been a number of attempts, and there still are. Hopefully, many will succeed. Dask takes the approach that rather than trying to build a distributed NumPy from scratch, we'll figure out how to just use NumPy blocks or Pandas blocks or scikit-learn blocks as the unit of data that I'm working on. So we have a distributed Dask array that is just comprised of NumPy objects. So all this should look very familiar to you if you have ever used NumPy or Pandas or scikit-learn. Similarly with Pandas, Dask takes the approach that I'll just have many Pandas operations, and I'll write algorithms that can operate on, many Pandas blocks, and I'll write algorithms that can operate on many blocks at once. Because Rapids implements, or because cuDF implements a Pandas-like API, Dask can use cuDF. Because CuPy has a NumPy API, we didn't have to change a dramatic amount inside of Dask to leverage CuPy objects inside of NumPy. To be clear, there was work that needed to be done, but most of that work was around generalizing what arrays are. And those things happen in the NumPy community. They've also happened inside of the Dask code base as well. Similarly for Pandas and for scikit-learn. So again, I can take NumPy, Pandas, and scikit-learn. And on the next slide, really just a quick change, I can now have a distributed version of Pandas and NumPy and scikit-learn, or CuPy, cuDF, and cuML. So Dask, briefly, is more than just big Pandas and just big NumPy or distributed NumPy. There's a lot of code a lot of very complex code in already existing code bases that look like this. This one happens to be Pandas, where we have some function that takes in some data in a model and it spits out some other data frame. You might write a for loop over many results, over a number of lists, and run these two functions and collect those inside of a larger list, some result. A nice bit of syntactic sugar around Dask is to let us create a task graph, create a graph on the fly. So we can annotate these functions with Dask delayed, and they become delayed functions. So Dask will lazily traverse all of these, this graph that you construct on the fly, and then the Dask scheduler will find where work can be done. So we've already added parallelism to an existing code base with just a little bit of work. Because I can do that, I can now take each one of these tasks can be executed on a node somewhere in your cluster. Let me see, this is, there we go. So your cluster is made up of parallel hardware. It either is a core, it's a multi-core CPU, it's a cluster with an even larger CPU, or a cluster with CPUs and GPUs. In the future, this could be clusters that have any kind of other hardware, and Dask should be able to fit comfortably within there as long as it can speak to that, as long as there is a Python library that can speak to that underlying hardware. We spent a lot of time within the Dask community thinking about how to deploy it. Many of these are open source projects, though now there are full-fledged enterprise companies built entirely around Dask, like Coiled or Saturn Cloud. Previous to those companies, we spent a lot of time thinking about how to leverage cloud-native tools like Kubernetes or ECS. There's things for Azure ML and things on Google as well. We've also spent a lot of time interacting with the HPC community and handling the variety and strangeness of batch schedulers like PVS and LSF and Slurm. I think there's even some drama deployment tools as well. Or now older scheduler or hardware schedulers like Yarn. We also have a good support for running Dask on those clusters as well. Sorry, I'm getting a little short on time, so I might skip ahead. So it was done purposefully that Rapids tried to kind of attack not attack, but leverage or engage the PyData community, and then use tools like Dask to scale those things out. Because we are or Python people, Python users need a lot of feedback. We also continued pushing on getting feedback of what's happening. So many of us actually that came from the Dask community to help with the Rapids effort. We're not GPU experts, but we knew a lot about all these other tools. Dask has a very sophisticated dashboarding system, as you can see in this previous slide that I can't get back to. Here. So Dask has a lot of dashboarding tooling to tell you about what's happening in the task stream, about what's happening per task, of whether I'm doing a particular read or merge, and give feedback to help users understand whether your workflow is performant and where it's slow. But as I said before, many of us didn't actually have deep GPU experience, and we needed more tooling to tell us what's actually happening on the GPU. We wanted a nice warm fuzzy feeling that when I did a GPU thing happened. And before, like there's tools like PyNVML that could tell you, or NVML that would tell you what's happening on the GPU. And it wasn't too difficult to just write a little bit more Python code, connect it up to dashboarding or to visualization tools like Bokeh, and integrate with JupyterLab. So now we can get real-time feedback about what's happening on the GPU, whether it's the utilization, the memory consumption, PCI throughput, really anything that NVML has to offer, we can visualize. We can tell you about the power consumption, tell you anything that the GPU actually tells its users. We can go query it and visualize it. And that's really great. It's so wonderful that all these tools actually can come together very easily for us to iterate quickly and build out these dashboards. Sorry, so when I said before, what we're trying to sell you on is not, or pitch is not just a fast merge or fast sort or particularly fast ML algorithm. It's really this end-to-end workflow. And this slide tries to break that down. This is for a mortgage data set, XGBoost training model where you're trying to predict house sales or rental prices, I think. I think it's the Fannie Mae and Freddie Mac, which is a standard data set for ML training. So we break this down into what it looks like for just reading in data. So just pulling data off the disk. This happens to be 200 gigabytes of CSV. What the XGBoost learning looks like, that the ML algorithm that you're applying to this data, and then stacking this all together. So it's not just a fast read CSV, and it's not just an XGBoost that's really fast. It's really the end-to-end that's significantly faster. And what we see is that with, in this case, the A100s are the new NVIDIA GPUs, but we even saw the same performance or similar performance with V100s, that we can get significantly faster performance and cheaper. So it's really like the most perfect kind of pitch. Like, here's this widget that's faster and it's cheaper than the competitor. But that's what we're going after. Within NVIDIA, within Rapids, we're very cognizant of the fact that GPUs are non-zero costs, that they can be expensive. So we are always trying to push for getting not just higher performance at a higher cost, but higher performance at a significantly lower cost than building out a similar pipeline with CPUs. Sorry, I'll go through these quickly. There's also a very sophisticated graph analytics Python GPU library that maps to NetworkX. This is the current list of supported algorithms. We're continuing to expand. More recently, we've been going after minimum spanning trees and continuing to push fast for more and more on getting better performance in PageRank. For visualization, we've also worked with Plotly and within PyViz to interoperate nicely with HoloViews and Bokeh, because we can pass data back and forth with QDF. And then more recently, there's been a very exciting development where people have built node hooks directly into Rapids. So no Python, just JavaScript and GPUs. So we can build really sophisticated visualizations that are just JavaScript or just Node.js. As I said before, the Rapids is rather expansive. These next two slides kind of show what we're trying to go after, where we think the maturity is, and the performance level, and who's currently using these things. So QDF, QML, we already covered. Briefly, QGraph, there's Rapids Viz. We're continuing to expand on other domain-specific libraries like cyber log parsing or analytics, image processing, signal processing, spatial processing, streams, recommender systems. We've done a ton of work this year. We have even more. We're trying to push even harder on more improvements with QDF. Those are both like, more improvements that are performance-based and also usability, going after things like better time series support. We have a wide variety of partners and adopters that expand both the contributors across the ecosystem, across the open source ecosystem, and adopters within business. We've also had a lot of uptake of Dask and Rapids within research and academia. So folks at Slack, MedOffice, Atlas at LHC. Unsurprisingly, Rapids has a lot of usage within NERSC and at Oak Ridge, where they built very large GPU clusters. At the bottom, I've included some links to Dask held a summit recently. And folks here like Jim Pravarsky presented at Dask in HPC and Dask in high energy physics. We can deploy on all these clouds. You can also engage enterprises like Coiled and Saturn Cloud for help. Please come join us. Here's a bunch of links to help get started. Thanks. I'm sorry I ran a little over. I might not have time for questions.
No, you're good. Thanks very much. If you can stick around we're at the break, but if you can stick around for maybe 1 or 2 minutes, we can go to Slido. I think you have the link, and we can try and answer a few questions there.
Sure. Yeah, so one person asks, ML frameworks usually have dedicated solutions for distributed multi-GPU, multi-node ML. Do you see this moving to Dask? Yeah, we see a lot of people that can do partial fits actually can leverage Dask ML very nicely. Within the QML group, they want to use, they often will write their own distributed GPU, own distributed ML solution, because they can be more performant than Dask, but they will still use Dask to help set up all of the networking and be able to, they actually have very challenging problems where they want to leverage networking tools like Nickel to do like all reduces that Dask currently can't do. But many people are still moving to Dask to write distributed algorithms, or at least write things that can work alongside Dask very, very nicely. Another person asks, how do these efforts compare with other GPU-oriented libraries such as TensorFlow, PyTorch? How are they meant to work together? Yeah, so the community, the PyData community has pushed on things like the CUDA array interface. So I can move data between different libraries with 0 copy efforts. So as long as your library speaks the CUDA array interface, I can move data between cuDF and CuPy and PyTorch. There's other things that you want to consider as well, like external memory managers. So PyTorch, unlike in the CPU world where NumPy kind of became the de facto memory manager as well as the compute engine, in the GPU world, everybody wrote their own memory management systems. However, people are now adopting tools and techniques to allow for external allocators. So within cuDF or within Rapids, there's a tool called RMM, the Resource Memory Manager. And we're asking or trying to help other tools like PyTorch, I'll come to TensorFlow in a second, leverage external memory allocators. So CuPy can use an external memory allocator. So we can not only pass data 0 copy, but we can also use one memory allocator across all of the libraries. We've not had as much luck with TensorFlow. They're not as, at least in my experience, as engaged as the PyTorch community is with trying to adopt standards that the community is trying to put forward. But other tools like JAX kind of have started to adopt some of these things. Yeah, another person very correctly points out that on the slide comparing strings, on this slide, that Pandas uses Python objects for strings, and they want to know how this compares with precompiled string handling. The answer is I don't know offhand, but I wouldn't be surprised if GPUs I would still expect GPUs to be faster, though I don't know how much faster. Precompiled string handling would be a significant gain for Pandas or for Python if that was ever adopted. But that's a more than valid point. And in many of the comparisons, we try to be as open about what's actually being compared. There's an old slide comparing cuGraph to NetworkX, for example, and that shows like bonkers performance, like 1,000 or 2,000x faster. And that's because NetworkX is Python only. There's others networking tools that in production use cases would probably use, even though they might start off with NetworkX because it's easy to use, but you'd go to something else for performance. But being open about that is something that is highly encouraged within the group. Another person asks, how easy is it how easy is the hardware to acquire / roll out? My usual issue is access to GPUs, to a GPU or multiple GPUs in the first place, even before thinking about using them efficiently. Yeah, so there is a tool. Right now we're pointing people towards Google Colab, which is here. If I click this link, this will bring me to a hosted notebook on Colab. This is just to get started. Many people are trying to, by many people, I mean folks like Coiled or Saturn Cloud. There's another company called, I think it's called Paperspace, that are trying to make, or at least demoware of, or one-click GPU accessibility a thing. So now that I have this notebook on Google Colab, I can change the session, no, that's not it. I can change my runtime type to GPU here, or I can actually ask for a TPU. The kernel will restart and it'll run anyway. Let's see. This time I got a Tesla K80. So I can, depending, and Google supports T4s, P4s, or P100s. Still though, we've been thinking, Rapids has been thinking about, and other companies as well, about how to make GPUs just more accessible in the first place. I think this page, rapids.ia/cloud, shows an overview of what is currently supported, how to get easy access to things like SageMaker or a single instance using with Dask. In the past few months, I've had trouble getting A100s on Google and EC2. I believe they've been purchasing more, so it's getting easier, but there's still some challenges there. We've tried in the Dask community to make this as streamlined as possible. So tools like Cloud Provider, where we can go ask to get a GPU on Amazon, can be done kind of seamlessly. I think there's maybe an example here. Somewhere in these docs, there's examples of getting to Rapids, but getting time, when I've done some testing on Summit, on ORNL, it's not been hard to get time to, so many clusters actually have very large GPU hardware locally.
So we should probably go to break so that we can still try and start the second session on time. But thank you very much for this great talk. We really appreciate it. And yeah, so I think you also addressed pretty much all the questions, but we'll still go ahead and migrate those over to the Slack for people who are curious. So once again, thanks, and we'll go to break now. Let's say that I think we originally scheduled a 30-minute break. Why don't we try and keep it to roughly 25 minutes? So we'll be starting just a little bit after the half hour.
I just wanted to quickly say thank you to the organizers, especially to Jim Povarsky for helping to organize and for inviting me. Thank you.
Welcome. And thanks for coming, definitely. This is great to see. For those of you joining us, we are starting at, as you can see from the timer here, in another 2 minutes. So starting 5 minutes after, just to make sure that everyone got a good enough break after the long and exciting morning session. And anybody knows where Jonas is? I've been trying to get in touch with him on Gitter. You're here. Good. Okay. Good. Then there you are. Yeah. Okay. You are now a co-host, and you should be able to share your screen. So if you want to practice that, we don't need the last 40 seconds. Great.
Hi, can you see it?
I can see your screen, I can see you, and I can hear you.
Perfect.
Everything is set to go.
Okay, should I wait another minute or?
Yeah, that last minute.
Yes.
But meanwhile, I'll be introducing you. This is Jonas Ashel, one of the author, or one of the primary authors of ZFIT. How should I say it?
Yeah, thanks for the introduction. And welcome everyone to this talk and tutorial on ZFIT and HEP sets. This tutorial will start out a bit inverted maybe, so we won't just go through all the basics of ZFIT and HEP stats and to use all these libraries like in itself. I will talk about ZFIT a bit, but then we will right away start out with some aspects of ZFIT that we can just take out. So as a core message, you don't need to use ZFIT to use ZFIT. You can just take out some of the aspects. That's a core part of it. So for those of you who have not heard yet about ZFIT or HEP stats, this is a project that's going on since a few years where we try to establish a fitting framework in Python that is capable enough to do high performance physics analysis fits. And the project hereby focuses on two aspects, which is on one hand, we need to be fast and scalable. So we cannot use, let's say, pure Python, we need something more. And what we mostly use there is TensorFlow or JAX in the future. So we need all these frameworks that do some real speed up that come from the machine learning world and that run also on a GPU. So ZFIT itself is quite performant, runs on a GPU, runs on multiple cores. And the second aspect is to have a well-defined workflow. As you see here, this is basically ZFIT in a nutshell of 5 parts. ZFIT consists of building a model, so it's quite a strong model building capability, of getting your data, creating a loss function or a cost function, minimize this cost function, and then have a result. And now these 5 parts are maximally independent. So this is a core part. The API of this should be as nice as possible, and it should be as decoupled as possible so that we can just jump in and get out of it again. ZFIT has the philosophy of we can't do everything anyway, so we need to keep things as accessible and let's say as separated as possible so that anyone can come, customize something, use their own parts, replace some parts of ZFIT. Now, to give you an idea, HEP sets then was built on top of ZFIT, just using basically these few models here, but it's actually independent. And the whole feature set, if you've never heard of ZFIT, is basically that you can build quite complicated models, multiple dimension composite model. You can create completely custom models, large, small. You can minimize the likelihood for especially unbind, also extended fits. You can include arbitrary constraints to it. And then if you get your HEP stats, you can do S-plots, S-weights. You can compute confidence intervals, limits. You can do significance calculation. That's roughly speaking the whole feature set of it. Now, I will give you an idea of what can is really mean in code, and then we will more focus on a few aspects, mainly about these aspects here, and just go in the later part of the tutorial into how to actually build models and so on, since this is rather new, and this works also with pure Python function. Now, setfit and HEPsets, just to give you a small example, would be we have a data set, a typical problem that consists of two parts. We have an exponential background here, and we will have a small single peak here. But that is maybe a bit too small. Let's see. That's what setfit and HEPsets are here for. So, building a likelihood with setfit and minimizing it. This is the whole part that we need to do. We will later on go through that more slowly and look at all these steps here, but roughly we have data, we create parameters, we create a Gaussian exponential, and we create a sum of it, then we create an extended ambient likelihood, we create a minimizer, we minimize that, and then we get our result. And this is it. So this is the whole workflow. This is how setfit usually looks like, how I would say every fit of setfit looks like. Some parts are more complicated and some less, but that's about it. And with these models built, we actually don't even need to minimize. We can, for example, try to find out, okay, if you want to set an upper limit, let's say the signal is too weak for discovery. So we can directly use now HEPstats, use an asymptotic calculator, so not toys. We can say over which space to scan, what is our alternative, and then just let it calculate the limits, and then we get them out of here. So that's about how easy it is to build something and to do something, and now we've done already a whole analysis using setfit and HEPstats. But before we go deeper into that and what we can do and what we can do with models and what we can do if you don't want to use TensorFlow, we'll first look at a part that is rather new, so generalized, which is the minimization, the API, and the workflow. So this, even if you already heard of setfit, this is quite a new feature. And the static also has a few rough edges still. Now, as I said before, you don't need to use setfit to use setfit. But as we've just seen before, was we build the loss and we build everything in setfit, and then we minimize it with setfit. Okay, fine, that works. But we developed now minimizer, loss, and result APIs that can also work with arbitrary functions and anything. Now, what is special about this API is that the loss or the cost function contains everything about the what was to minimize. It contains a function to minimize, it knows about the parameters that it depends on, and it knows about constraints. So this is not for the minimizers. Linear constraint is anything that comes only to the loss. Then we have a minimizer, which is stateless and can be replaced by any other one. All that it does is that one function that just minimizes our loss. And from that out, we get a result after our minimization, which stores all the information about the fit or the minimization itself, and it can also do some uncertainty calculations. This again is decoupled from the minimizer. So these are three steps that we will use. We won't directly need to think about all of these, but this in your mind, if you think how to do that or what can I do, or what can't I do, this is the separation, and this proves out to be quite powerful. So let's start out and just use setfit to minimize a function. What we first do is we just set the autograph mode off and the graph mode off. This means that setfit doesn't rely on TensorFlow. Now we can use pure Python, and it's like any normal Python library. You can forget that there is setfit and then TensorFlow behind the scenes. Now, what we do here is we can just create a small functional problem. Then we set the error def. So what is the error definition, for example, 0.5 for a log likelihood typically, or 1 for a chi-square. If you're aware of the I-mini cost functions, that is pretty much the same interface. And we get some parameters. Then here, what we do is we create a minimizer, and we just say minimizer that minimize this function. And in the end, on that minimized object, so this is the fit result, we can call, for example, Hesse, which calculates the Hessian uncertainties, or we can calculate errors with something like profiling, for example, minus. Here we use minute minus, and then we get the result. Same as we got before when using full set fit. So this may be for some of you who know set fit quite new. We can minimize arbitrary functions, just Python, NumPy sums, nothing special on that. The interface of set fit is intentionally built that way that we can use it more general. Now, seeing that, I would assume that someone of you may have the thought of, well, why do we need more minimizers? Isn't that covered already? And that is a good point, because there are many good minimizers out there. Absolutely. Implementing just a new algorithm or trying to outsmart all the others, that's usually not a good way. There's not so much to do it. So setfit just wraps existing minimizers with the goal of a clean interface and behavior. And even that would need quite some reason why would we wrap them and have a new interface in that. And this is basically because we want to have two essential parts, and that is, some libraries have different choices on that. And one is that you first have the configuration of a minimizer. Whenever you minimize something, an algorithm, be it something like Adam or one of the TensorFlow minimizers, be it something that uses approximate Hessians, be it something that uses trust regions, they all have a ton of configurations. And these should all be in a separate function call so we can just build our own minimizer and we don't need to care about any other existing minimizers. And then there's the other part, which is the minimization. Every minimizer should have exactly one well-defined method that minimizes a function fully, that is stateless and doesn't change it. And this more functional approach of having just one method that is stateless has quite some advantages if you start decoupling things. So then not depending on a state means that other libraries that use setfit or a minimizer, they always know, okay, I can just call minimize and everything is encapsulated in there. I don't need to do through certain steps. So this means this design choice, this has led to two design choices. On one hand, every minimizer is its own class, and every minimizer is basically one method minimize. So it's an absolutely simple setup, but it led to a few powerful conclusions or API adaptations. Now, to mention, this is not an obvious or a possible choice. For example, iMinute, which you may know is a stateful, so you can massage around the minimization and you can continue the minimization and so on. This is not directly possible with that, but it can always be encoded. We'll see later on in custom minimizers. And there are other things like SciPy, which mixes both of these functions in one, which then leads a bit to a cluttered interface and a few issues in the docs and very hard to find bugs because every minimizer needs to care about the other thing. And when looking around about all these minimizers, why we start wrapping them is because most of these minimizers, they do not offer the combination of having automatically a gradient, allowing for arbitrary constraints, having the same termination criteria. Like SciPy in my minimizer, they have all of the different termination criteria, and that they can do uncertainty estimation. So this is usually if you want to do that by hand, these four things, this is basically always, I think iMinute fulfills most of that. It needs to be done by hand, which is saying we didn't even need to calculate the gradient or something. This is all done automatically. And this is basically the role that setfit minimizers fulfill. They just take care of everything that you don't want to take care explicitly and leverages the power of a minimizer like SciPy to support all the other things, like arbitrary constraints or the same termination criteria and uncertainty estimations that we'll need in high-entropy physics. So let's have a look at how these minimizers look like and how to use them. So every minimizer takes, in principle, arbitrary arguments to be created, whatever it is. But of course, we try to unify them and just use the common language for the one that are there, which you see here. And here we can create a minimizer of our choice. Feel free to create whichever one you like. They should, in principle, all work. And there are many more. What is interesting is something like PyHEP, maybe. Mac users pay attention. This does not install easily, which is another powerful library, or the NLOP library can be used. Now, these minimizers accepts anything that has a function and that takes an array of values to evaluate, and it doesn't attribute error depth. Needless to say that if you build your loss with setfit, you automatically have that already. Let's have a look at a small intermezzo here. iMinute, I think, is named by many of these, and it's also wrapped in setfit. Now, what we can do is, we know that iMinute accepts the same functions, right? It uses also these positional arguments of array, and it has an attribute error depth. So we can also just use our exactly same function from before that we just use and minimize the thing with iMinute and the loss that we used before. So that this is this is the loss. This is a setfit loss now. So we can directly take the loss that we created up here in this more complicated example, which we will later look into it. That we minimized, we can also just pass that directly to iMinute instead of using setfit, because iMinute accepts the same functions as setfit does, or let's say the setfit loss. Yes?
Can you make it a little bit bigger?
Oh, yes. Let me see.
Which one? Thanks. Control plus should work. Yeah.
Yeah, is that better?
Yeah.
Okay, perfect. And otherwise, you can always follow us a notebook on Binder if you click the link, or download it for yourself if you want. So we see Minute directly uses also can use setfit losses without any change. Going back, we've seen how to create a minimizer, and then we talk about the minimize method. So it takes exactly 3 arguments. On one hand, loss, which is the function that it needs to minimize. On the other hand, the parameters, which is information about the parameters, so where to start, and we see here we can give more information actually. And they can take an optional argument, which is a fit result, which is a result from a previous minimization that contains additional information. And these 3 arguments seem to be able to they contain everything that is needed to do all kinds of minimization. Now, what we see here, we can have a bit more fine-grained control. We can either directly use a dictionary that contains additional information, or we can create setfit parameters. For those of you who know it already, that just essentially are the same. They just contain a value, they contain limits, and then use this to minimize our function. If we have our function again before, we use the parameters with more info, either this dictionary or the list here. We can minimize it, and we got it. And we see now we use type. We also see that this all looks exactly the same as before, and that is very intentional. So minimizer of minimize is the same as when we used minute, and the result looks exactly the same when we use minute, just we're using SciPy now. One crucial thing here is, though, as you will maybe see, is the EDM here. We have to estimate the distance to minimum. I think this is also familiar to anyone of you who has ever used minute or iMinute in Refit or iMinute package. And this is one of the challenges as well, because many of these minimizers have different convergence criteria. And that's why they actually take in setfit a criteria, which is by default the EDM. This means that if SciPy now converges, sometimes this also converges too early by the standard criteria. If SciPy converges, it means that it converged the same criteria as iMinute did. This means done by rerunning it in case it didn't find the minimum and make sure that it's over the estimated distance to the minimum. However, this can also be a completely arbitrary criterion. And this is something, since it's a rather new feature, where we're looking out to add new criterion, because calculating the EDM can be rather expensive, especially if you don't have the proximate hashing calculation. However, with that, we guarantee that whichever you use, NLOpt, SciPy, IPOpt, iMinute, they all use the same convergence criteria. And now we come to the last step, which is the fit result. The fit result is something that also exists out in the wild, like the optimized result from SciPy, but setFit is a bit more powerful because it also needs to contain the uncertainty estimations. And these are the flags that the result contains, or some of them, whether it's valid, whether it's what's the minimum value, what are the parameters, on some general information, which is more or less of a free field. We contain always the original message, so in case someone wants to look through it, we don't encapsulate things here. Now to do uncertainty estimation, we can use HESE. And here setFit has two possibilities. On one hand, it can use the exposed HESE method from MyMinute, or it can use a custom implementation in pure Python, which is completely independent of iMinute. If we now print our result again, we see that these uncertainties have been added here, and we see minute HESE and HESE NumPy, they agree, luckily, very well. We can also use a different confidence level if you want. We don't need to use the default one. And we can also give a different name. This is just by default, it takes the name of the method, but we can also just call, we can do another uncertainty estimation at 0.9 confidence level and call it differently. And if you printed that again, we just see all of these errors added. The second method is a profiling method, which is like minus. And there are two again. There is minute minus, which uses the exposed minus method of iMinute. And there is setFit error, which uses, again, a completely independent method that does profiling and yields, though, as you see here, the exact same results. Again, this also supports different confidence levels and so on. So we see now these are the three main steps that you can just use in the wild to minimize something. And it means that we can now leverage any SciPy minimizer and just calculate, because remember what we've done here, this is a SciPy minimizer. So we now just got a minus uncertainty and the Hessian uncertainty on a SciPy minimizer that terminated with the estimated distance to minimum criterion. So we get now everything in there, with actually a function that we didn't specify the gradient for. And we can just change one line of the code, go up, create the different minimizers, and everything runs exactly the same again. That's exactly the intention behind it. Now, what did actually happen here? So the function that we gave to minimize, that pure Python function, is actually wrapped in a simple loss. And the parameters were converted to a setFit parameter if we didn't do that before already. We can see that here, because the result also still calls the loss and the minimizer. And now we get the loss that was created. So a simple loss is just something in setFit that allows easily to wrap a function. These are the parameters. If you say get parameters, you get all the three parameters of that loss. And we could also do the same thing as the minimize did by using the simple loss from setFit and say, this is my function, these are my three parameters, and this is my error definition, which is basically the same. So you can also directly use this to do setFit minimization. Or you could also use that directly for iMinute. Now, there is a third argument to minimize, which we didn't talk about, that is the init. Now, these are the parameters that we have now lost. And what we can do is we can now take the output, the result, and use that as an input to a new minimize. So we can chain minimizations. Often you don't need that, but if you want to do first, for example, something more global and then take the result of that or something along the line, or be more precise with a minimizer, this can be used. And the contract is that a minimizer can't just use everything that is contained inside the result, which is maybe not exactly, but it's a good approximation. It's a good starting point for the minimization, and that can help a lot others. So we here create a second minimizer, now a minute, with a tolerance that is a bit higher, lower. We minimize, and we see here, we give the result. as a shortcut, if you just want to say continue this minimization, we can also just call minimize with a fit result, in which case it automatically takes the loss from the result, the parameters from the result, and the information from the result. And we see here we get actually better values here. Now, we go to the last piece of the minimizer tutorial, which is creating a custom minimizer. As the philosophy of SetFit goes, it wouldn't be a real SetFit feature if there wasn't a straightforward way to just implement your own. Of course, one could just imitate that interface, but SetFit provides base classes that do all this heavy lifting. That's the main idea behind it. It has pieces to help you with it, but it shouldn't enforce that you would need it. And this is a minimal example of making a chained minimizer. So we just take here a list of minimizers. And what we do in minimize, this is also another SetFit convention. If you want to steer the behavior of a public method, then we need to override the underscore method, minimize, and it has the same, usually same call API. And then what we do here is we just say, okay, minimize and minimize. And again, this has surprisingly the exact same interface, and we can just use now our custom minimizer to minimize that, which changes this through these two minimizers together. And we got our result. Again, same standard. We can do uncertainties. We can do whatever we want. Just to mention, if you want to have something more powerful, it was just chaining. There are also useful helpers inside the minimizer class. One is an evaluator, which is like a loss function, but it is a bit easier because it takes care of the maximum iteration and automatically handles that. It takes care of NANs, of the strategy, of callbacks. And there's also a criterion which you should create if you use it, and you can see how it is. So just a few helpers to easily create your own minimizer rapid. So in summary, what we've seen here is SetFit offers standardized minimizer interface, and in a way that it decouples the uncertainty estimation and also constraints from the minimization process. This should be an implementation detail behind the scene, but declaring it as a user, it's decoupled. Currently in SetFit, we have MLOps like PyIMinute, IPI, and TensorFlow optimizers wrapped, but there can of course be more added. And yeah, it's a bit of a new feature. You can't complain about parameters that already exist, and it can be slow with many parameters if you don't have an hash approximation, because we just have the EDM criteria. But any inputs or wishes for that are more than welcome. So in case someone has questions on that, then you can see in Slido maybe. If someone has something specific on this. And otherwise, we continue to get a...
Jonas? How
yes?
about you move the Slido window into the sharing, so that, because there are quite a few questions there.
Yes, I'll do that. Sorry, that was the wrong button.
Since they're both web browser things, you could just put the tab
I can share.
into the other tab. Here, I'll give you a link. Oh,
I've got it.
already given you a link.
I've got it here. Okay. All right. So that's a very good question. Yes, whether the parts might factor those out in the standalone projects. Yes, exactly. So then we already do that a bit by, for example, factoring out there's a standalone package SetFit physics, which is for any physics functionality. So in the core, we clearly don't want to have that, but we still want to have a place where people can contribute that. And in my mind, there is more of like a SetFit models and the SetFit minimize part. Also, some parts already naturally factored out, such as HEP stats, which is a different name, it's a different library, and it just uses the interface of SetFit. But for example, if you want to do anything confidence interval and such stuff, it's not in SetFit already. So yes, this is a very good point. And we also have already a SetFit interface and so on, exactly to get that. This is indeed the future plan. For the next question, the checks backend. Yes, so this is something that is, I would say, actively worked on. For example, we also Maybe you're going to see that in the a little bit later on in the talk. For example, what we did was we converted most of the set for the internals and now make it also public, a NumPy-like API to the user. So the TensorFlow NumPy wrapper, but so it means that it's way easier to change the backend. Currently, there are still a few blockers on the road that are not quite clear. So one thing is like global parameters, how to handle that, and how to, yeah, that there are just a few things where TensorFlow seems a bit more advanced and features that are a bit missing in checks. But this is, I mean, this is something that we actively work on in the sense of we're quite convinced that the future is checks in the end. But we also have to see how checks really develops and how it interoperates with TensorFlow, because it currently does quite well on that, actually. Or it goes into a direction of that.
Before the next question, can you zoom in on the screen, just like you did with Jupyter,
sure.
Read the questions?
Of course. Of course. So the question was about the checks backend. To mention though, yeah, no, this is really for the backend. It's okay. Then it was set to minimize the status, but it looks like the Hesse and error computation happens later in a result object with state. That is true. And this is the difference though for, so this is a design question that one could in principle also think, should we return every time a new fit result? Now, the fit result is a bit different from the minimizer. So the minimizer itself is stateless. The fit result in this sense is not. But the fit result, there is no part in this sense which depends on the state, except that you have already calculated things or not. But you cannot, so if you do, if you execute the method, this does never depend on previous executed methods, except that it's maybe a bit faster or not. But if you want to calculate an uncertainty, it will always calculate the uncertainty and you will always have the same answer because you cannot change the minimum. All you can do is add additional information, so to say, to it, but this does not influence, in this sense, anything else. That's the idea behind it. The next question is, what does EDM refer to here? So the EDM is the estimated distance to minimum, which is a metric to determine how far we are from the minimum, and that iMinute famously uses. And I guess this is something like the gradient times the inverse of the Hessian times the gradient trend base, I think. I'm not entirely sure, but it tries to guess how close it is to the minimum. So the errors and the loss, you say, are not decoupled. If you change from NLL to 2NLL, then the prescription for error calculation needs to change to compensate. So yes, the error calculation and the loss, they are decoupled as they just talk on public interfaces with each other. Because if you change NLL to 2NLL, you're very welcome to implement that. Then you need to change the error definition of that loss, which every loss has, to 1. And that's all that the error calculation cares about. Basically, it's a function and it's the error definition. So, I mean, these parts, of course, need each other. You can't do error calculation without a loss, but the loss needs 2 parts. It needs to be, callable, basically, and has an error definition. And then, so all the information that is needed is publicly, and they should speak only on public interfaces and minimal interface to each other. And the last question is, could you comment on scalability to include many models like voice-done analysis for physics measurement? Is it robust for many PDFs at once? Yes, that is in principle doable, everything. So this is completely scalable, I think. In the end, it's just a wrapper around other minimizers that tries to bring more stability and uniformity in it. But if you want to do physics analysis with it, then and use PDFs, I mean, you can try it out. And that's, I think, my best suggestion. Try it out and see how it goes. Then maybe you anyway want to use full set fit, which then would lead me to the next part of it. Now, let's see, this is the next tutorial. And these tutorials are also online, so I will rather say a few things about it, but this is rather a fast tutorial since we have already seen most of the parts before. So SetFit, as we know, has these 5 parts, and we've seen mostly already the last 3 parts, especially the last 2 parts. Now let's have a look at the other 2, model and data. So data is something in SetFit that actually is a very small feature. We just define with a space, or like with an axis object, basically what are the limits of it, but rectangular, we want to keep it simple. Then we just load the data inside, and data object in general can't do anything. If you want to do pre-processing, use pandas. If you want to load it from root, you can do it directly with SetFit, but it's just a path through for uproot. I mean, use uproot there if you want to histogram it. If you want to do anything, then there are enough libraries as we've seen. So SetFit doesn't really do anything else with data except of wrapping it into standardized format and knowing about weights. The more interesting part is building the model, which is probably the strongest part of SetFit. Now, the model, when talking about the model, we usually mean a PDF, probability density function that is normalized over a specific range. The specific range where it's normalized about is called the norm range. And the whole model is parameterized by parameter objects. This is a design choice, and there are maybe also additional possibilities in the future where you're thinking about that as more functional. A parameter object has a name, a unique one, and has a value, and maybe has some limits. So let's just see how these objects work themselves. We can create a parameter, and this is in this sense a global object. That is, if you change it, then it will change everywhere that we use it. We can also change something like floating or not, which is just a hint where to use it. And then we can create a PDF by using the same observables that we created before for the data and giving our parameters. Now this has a number of dimensions. This has the observables and the space and the norm range, which usually are the same, but in principle we could change the norm range. This is just a default space, which is a good hint of what the PDF usually likes to see. And we have a params attribute which contains the parameterization. So the mu of the PDF is the parameter which is also called mu, and sigma of the PDF is a parameter we call sigma 42. If you just want to, in general, get all the parameters of a PDF, because a PDF, these are the direct parameters. It could also be that we have PDFs of PDFs. Then we have a functionality called getParams, which returns us all the parameters that a PDF depends on. In this case, of course, mu and sigma, they are the same. But for example, if we would use mu for both mu and sigma, here we create a Gauss, and then say .params. The params will tell us, okay, mu is parameter mu, sigma is the parameter mu, while getParams will just return us a parameter mu, a set of all the parameters. And this is already a simple way of how you want to share parameters. You just use the same parameter again. Now, a PDF in SetFit has a few useful methods, which are main feature. On one hand, they have a PDF function, which returns the PDF value. They have an integrate method, which integrates over the PDF, and a sample method. This is basically the core of any PDF. As you can see here, we just integrate, we get the integral. The things, what we get back here is called tf.tensors. But don't be afraid, this is like a NumPy array. I mean, now with checks and torts and all this coming up, they all have their own version of tensors, which are fully compatible usually with NumPy. For example, we can say np square it, and we get NumPy array back. We can also sample from the PDF, or we can use the PDF functionality given our sample. All how we would expect that. Plotting is an aspect that we of course need with PDFs, but it's not really directly available in purpose in SetFit, because SetFit is only model building and the minimization part, and all the rest is to other libraries. But with libraries like Matplotlib or PyHEP, even this is not a difficult task at all. Now, SetFit offers quite a few models that we can choose from, crystal ball, low crystal ball, and also allows to create a custom one. So let's just see an example now with something more realistic as was asked before as well on a more complicated PDF that we can have. We could create a mass observable. We can create a few parameters, mu, sigma, and then create a crystal ball function, maybe more realistic for a signal. Then we can create something for the combinatorial background. So an exponential, for example. And we can create a KD, kernel density estimation, just from some partial reconstructed or something. Let's say we just have something where we do not have an analytic shape for, but we want to model with a kernel density estimation. Now we have the three parts. We have a signal component, modeled by a crystal ball. We have an exponential background, combinatorial background, and we have a kernel density estimation for a part that we take from simulation. Now, the final model will be the combination of the three models, the mixture, or the sum of it, which we can do using the sum PDF. Now, if you do a sum of PDFs, we need two fraction, and then the last one is 1 minus the sum of this. Or we could also give all three, and then we just need to make sure that it doesn't run over something. Now, we can just change the values of these parameters. We can, for example, now create a sample from it, just to see how that looks like with slightly different values. So what we see here is the sample that is generated in orange, and in blue, it's the sum of the model. So clearly, this is not yet fitted. We can also just, a small modification, get all the components here nicely plotted. Now, often we are also interested in the absolute yield of a data set, and for that we can also create an extended PDF. Extended PDFs in SetFit are handled in a way that the philosophy is, if a PDF is extended or not, it does not change the behavior of it. So a function won't just give you back something else. The only thing is that if you extend the PDF, there are a few methods available, a few additional functionalities available that will just raise an error if it's not extended. But there's no magic that the PDF scales automatically or something like that. For that, SetFit has special methods which are called extended PDF or extended integrate, which is a PDF multiplied by the yield. The yield is what we call usually is the amount of points from that species that we expect to see with that PDF. Now, one additional thing is if you have just extended PDFs and we create a sum, for example, then we do not need to tell the fractions automatically will be taken from the yields. And you can do this by creating a new one, which creates a copy or set yield to set yield in place, which is a choice in case the copy doesn't work properly. For example, for a custom model, this can be the case. So there are two ways to create that. We can take our model and then create an extended model of it, or we can create the model extended. So for example, we create an extended signal with a signal yield, we create a combinatorial background with the extended background, with the background yield and our trico yield, and then we just create a sum here of all these three models. Since all of them are extended, this is fine. And now we come to the more familiar part. We have our data, we have our model built. To the loss that we've seen before, instead of creating an arbitrary loss, we can just use, of course, predefined ones such as an unbinned negative of likelihood, or also an extended negative of likelihood. An extended one takes yields into account, an unbinned one does not.
At this break, I'd like to point out 5-minute warning.
Say again?
5-minute warning.
Oh, yeah, thanks. So the loss contains typically model, data, and all the constraints that we have. And we can also, as before, get all the free parameters here. An extended loss is just created with an extended unbinned negative of likelihood. We get parameters. So for the minimization, we've seen already many things before, but we can just minimize that. We can fix parameters first. We can say, okay, this is not floating. We can minimize it, same as we've seen before. And we can also then just plot the model. And we can do exactly the same things as we've done before. We get our fit result. We have our parameters, and we can do estimate the uncertainty, exactly the same things that we've already seen. I guess there's not so much to say on that. So, and now after that, we've just now created a model, we composed it, we have used that to minimize it, we can get the result. As seen before, and we should not forget HEP stats. Now we can directly use HEP stats with that model that we created up here. We can do confidence intervals, for example, by creating a calculator. There's the asymptotic calculator or the toy calculator. Toy calculator needs a bit more time, but it does properly toys. The asymptotic has some asymptotic assumptions in there. And we can create a parameter of interest array and then get an instance that calculates confidence intervals. And we can calculate the interval of it. The same way we can do S-plots, we can do S-weights, and so on using HEP stats directly together with setfit. Now these are the basics of setfit, and I want to point you to, yeah, as we see here, the noise plot. And what I want to point you to is two additional notebooks if you want to continue it. On one hand, you can see there are setfit tutorials available that you find on the page. And on the other hand, there are two tutorials which I think are quite relevant. On one hand, this one is about custom models. So if you want to create a custom model, it's as difficult as doing it like that. You can just implement the function and we get a PDF with everything available with integral, sample, probability. Try it out, just implement your own function, see whether you can do it, see whether you can do the same game as before. And you can also do more complicated models such as an angular PDF that we took from an analysis, which is 3-dimensional, contains fits a few angles. And that's as hard as it is to implement it. We just take it and we use things like np.cos, second which is, Matthew, your question before on moving forward, this is exactly part of this, switching the API to a generalized NumPy API. Also, if you say now, well, okay, you don't want to use setnp, you don't want to use TensorFlow and stuff, you can also just use pure Python. There's a section on that, which tells you how you can wrap it, or you can do this matrix switch, graph mode off, autograph off, and then you can use pure Python, NumPy, Torch, JAX, or interface with any Fortran code, or whatever you want in your model. So models are quite flexible. If you're interested in this part, this is the tutorial for you. And there's another tutorial which shows a more realistic measurement that contains information about constraints adding it. So Gaussian constraint, for example, this is one way of adding additional information. We also see this is more realistic in terms of signal background, in using other packages like particle and tap units that play very nicely together with ZFit, of course. Or to do simultaneous fits, to add different information from other channels, which is just to show you nothing else than we just create two losses and we add them and we have a simultaneous fit. And then everything is again the same. I mean, minimize the loss, something you know already. We just create two models and fit it to two different data sets. And this goes further with a discovery test in HEPStat, so we can see whether here we fit the rare mode and the resonant mode at the same time, sharing some parameters whether we actually have a discovery or not using HEPStats.
Okay.
This was the talk about ZFit, tutorial and HEPStats. So let's go to the Slido questions. That's a good question. And because this is something that is since a long time on our list, and we tackled that. Short answer is no, currently not. But this is something that we try to tackle in different ways and had people even working on it. And you can always do it partially. That is not so hard to do, especially because you can just write your own configuration super easy with just having a dictionary or something like that. But there is no out-of-the-box way currently to serialize models. But it's very much something that we try to figure out how to do it in the right way. And I think there are also other projects that do that. I mean, like PyHEP does it very successfully, or I think Carpentry and so on. It's this kind of how to dump and learn something that we hope to be really to kind of improve. Yes, so that's a very good question from Jim with the ordered dicts. Yeah, that is actually more of a it's true. Now all the dicts are ordered and they can be replaced. We just very recently, I think, switched from 3.6 to 3.7. We kept there before the dicts to make it clear the intention on it. But that is more of an old thing. Nice check.
Same as before. Can you read the questions? Thanks.
Oh, sorry. I'm sorry. Yeah. So is there also binned NLL? Short answer is no, not yet out of the box. But this is something that we also work on quite a lot, and as Henry also mentioned in his talk about boost histograms, we now boost histograms out and having their nice interface. It's just a matter of time. So we work on that. We have multiple branches actually to get it binned. Though it's quite easy to do a bin. So you can't use that out of the box, but I'll have quite a few colleagues actually which just use it like that, because you can build your model and your PDF with ZFit. Then you just write your own loss function, as we've seen in the beginning, which takes a ZFit model and bins that and takes the bin data. And then you just use a custom function to minimize that. So unbinned NLL, no, the question is unbinned NLL a wraparound iMinutes function or something completely different? I think you refer to the cost function of iMinutes, right? So no, not at all. This unbinned NLL is completely custom implementation. In fact, the iMinute cost functions, I think they are quite new. I think they're like half a year old, and ZFit ones are already since years around. No, these are two different ones. And the unbinned NLL, actually, I think the goal here is to have more knowledge on things. So, for example, to remove constants, to have gradient information, and so on. So while they have a similar interface, they try to fulfill different needs. And I think the iMinutes cost functions tend to be a bit more lightweight. So thoughts about interoperability with RuFit or PyHEP-based models? Yes, that's a good question as well. And yes, there are quite a few thoughts around. Actually, with PyHEP, we're also in context. When we started out, that was one of the first things that we talk to each other because we both use similar backends, we both use similar projects, but it's also clear that, for example, PyHEP really has a different focus on all these binned models, while Cepheid focuses more to get unbinned models right. I think interoperability with Roofit can be a bit critical, maybe on the loss function, but really having the same models and so on, it's a bit tricky because some design joins are quite different. And with PyHEP, I think as soon as we get something more with bin stuff and stuff, we can see what we can put together there. But we're already we have this in mind and sometimes talk. That's it. But I think it's for the short and maybe the medium future. It's not directly addable, except you create your own function where you just add the two losses or something like that. So the next question is, when implementing a custom PDF, are there mandatory functions that have to be provided besides unnormalized PDF, like the CDF, for instance? Very good point. And the answer is no. So I would say, except you need to specify what are your parameters or write the init, because so that you know what's the dimensionality of your function, every parameter it takes. Let's say init, yes, or say which parameters are, but you don't need to provide the CDF, you don't need to provide the inverse CDF or something like that, which is one of the things of this base class of Cepheid. They take the heavy lifting. So the normalization behind the scenes is done numerically if you don't provide that. The sampling is done with accept reject if you don't provide that. So you just need to implement the unnormalized PDF yourself. You can always implement them. You can register analytic integrals. You can completely override the integrate function. You can completely override the sample function, whatever you want, but by default. Or you can also just directly override the underscore PDF function, which means, you know, you take care of the normalization. If you want that, if you want to cheat your PDF and scale it up or scale it down, you can always do that. But the unnormalized PDF just takes the line shape and everything else should be done. Next question is
Actually,
yeah.
Since it's 10:30, maybe we should move the questions to Slack, and please do answer them in Slack. And those who are asking these questions, check there for the answers.
Okay, sure.
Great, thanks.
That's good.
So, well, thank you for this great talk. It was fantastic.
Thanks. Thanks.
I learned a lot. Yeah.
Thanks for giving the opportunity and organizing everything. That's really amazing. Thanks a lot for that.
Our next speaker is Santam. He'll be talking about awkward array testing. Actually, the rest of these from here on out are lightning talks.
Yeah, so I'm gonna share my screen.
Sounds good.
So you should be able to see it.
Yep.
So yeah, so hi everyone, this is Santam Chaudhary. I'll be speaking about automating awkward array testing. So first of all, let's have a look at the different layers in awkward array. So right at the top, we have the different Python bindings of the C++ classes. That's the layer with which we interact. So after that, we have the C++ classes used for data navigation. And below that, we have the CPU and the CUDA kernels. Now, these contain various kernel functions. So when you try to enter any sorts of array and do functionality on them, so that's the place where all the array manipulation take place. So after this, the rest of the talk is going to be based on the testing on these kernel functions. So this is the current testing infrastructure that's there in awkward array. So we have a kernel specification file that contains various arguments like the kernel function name, their arguments and all. And we have a script called generate test.py that's present inside the dev folder. So when we run this file, so it's going to take in inputs from this kernel specification and it's going to generate a Python kernel here. Now this Python kernel is not a standalone kernel as you saw in the earlier slide. It's just a temporary specification that is generated in order to automate the testing in here. So this is a snapshot of the kernel specification. We've got a kernel function, bit mask array to byte mask array, and we've got all the different arguments, the argument name, the type, the role, and dirt. Below that, we have the function definition. This is one of the auto-generated Python tests. So we have all the inputs in here. Now these inputs are hard-coded in the kernel specification file. So the script takes in these inputs and passes it through the Python kernel and gets back the output. And then we have the expected output in here, as you can see in line number 13. And then in line number 15, we again pass these inputs into the kernel, and then we assert whether the result given by the kernel is same as the one we are expecting here. So the one we are expecting here is the one given in line number 13. So the question is, does it cover all the test cases? The answer is no. So what are some of the loopholes in here? There are not too many specific test cases. The testing is not error specific, and the roles of the arguments are not well defined. So what can be a good solution to fill up the gap? We can use something called property-based testing. So what is property-based testing? Property-based testing is a type of testing in which we define the properties of the input and the output that we are expecting. So what are some of the advantages of property-based testing? We can have more hard-coded input data. We can test a larger section of the code base with a very little amount of code, and it's highly efficient and flexible. Hypothesis is one of the greatest examples out there that facilitate property-based testing, and it has tons of features like various strategies to get constraint-based data. We can have highly elaborative test results, regenerate failing test inputs, shrinking, and much more. So here are the different workflows of how a unit test is different from a property-based test. And as you can see, in the first step, we are hard coding the input data in the unit test, whereas in property-based test, we are defining the properties and we are letting the computer decide which inputs to generate based on those properties. So here is a sample unit test. We have a sum of numbers that takes in two arguments and it returns the sum of the two arguments. So below we are passing in 2 and 3, and we are asserting whether the result given by the function is the one that we are expecting. So here the output that we are expecting is 2 plus 3 equals to 5. So a similar unit test can be written in property-based in this way. So we have many strategies, as you can see in line number 9, where we have defined that the argument 1 and argument 2 are both going to be integers. And it has some properties like minimum value and maximum value. So based on these properties, the code is going to generate various inputs and is going to pass in these inputs to the function sum of numbers. So the plan is that we are going to have a CPU kernel function and pass in these generated input values, and then we're going to assert that the result given by the CPU kernel is same as the one that we are getting from the Python kernel. So in that way, we are going to know that the Python kernel and the CPU kernel are both working fine. So if one gives an error for one input, then the other has to give the same error for the same input.
So, Santam, 2-minute warning.
So when we run this, we get a highly organized statistical data, and we get like a lot of things like the runtime, the number of failing examples, the passing examples, and so on. So here is one of the approaches out of the many approaches out there that we can implement hypothesis to generate the other corner cases out there that is not there in the unit test. So we have a constraint.json file that stores in all the argument strategies, and we have a script called generate strategy test.py. So it takes in these strategies as an input and then passes it to the Python kernel, and then we hard code the input and the output. So after that, we're going to run the C test and the Python test, and in that way we can indirectly check whether the C kernel and the Python kernel are both giving the same result. So this is an overview of the talk. So unit tests may have some corner cases untested, which can be found out using property-based test. And awkward array creates a Python kernel, which is a specification used to auto-generate tests. And the hypothesis library can be used to get a well-documented result of the test cases. I've listed some resources. You can go through them to know more about this. So I would like to thank Jim and Yana for helping me out and being a great mentor to me in this. So thanks a lot. If you want to know more about this project, you can contact me on this email, or if you want to know more about the work that I've done, that's my gift. Thanks.
Okay, thank you. Questions? If you have any questions, type them up on Slido. All right, must be super clear. Thank you, Santam.
Thanks.
Next will be Andre.
Hi, can you hear me?
I can hear you.
Okay.
Can you share screen?
Okay.
There you go.
But,
So maybe you want to increase the volume or the gain on your mic or get closer to it.
oh well, let's see. Can you hear me now better?
That's much better. Thanks.
I sometimes it's a little finicky. Okay. Hi everyone. So I have a short update on the status for NPL HEP, which I've presented in the past, and the fundamental functionality remains similar. So this is just going to be a refresher. So primarily, the primary task for NPL HEP that was envisioned was delivering easy publication-grade styling for Matplotlib HEP-based plots, and this is achieved by distributing style sheets and fonts, and thus saving real analyzer time and sort of streamlining the workflow a little bit. However, as this was developed, we realized that there were some domain-specific functions, or rather specific ways that we needed some of our plots to look that were beyond what was contained in Matplotlib, and so we added some modules for extending this. However, the maxim here is to align with the Matplotlib API to as much as possible to be intuitive and to not really cause any disruptions when users search for problems, such that any answer you might find on Stack Overflow still works without any issues. And secondly, we would also like to upstream as much of this as possible, again within limit. So actually, thanks to this effort, Matplotlib now has a basic histogram plotting support, as in the differences as opposed to hist, which was operating on a list or an array of data, both calculating and plotting the histogram, which made it somewhat difficult to plot histograms that were already pre-binned. So there's a new function in matplotlib called stairs that takes histogram values and edges. But nevertheless, some of the functionality remains a little bit too specific to be upstream, such as plotting histograms with error bars, which doesn't seem to be something that could make it up to matplotlib. So let me just import matplotlib and numpy and take a look at the default example. So taking the usual numpy histogram by passing some array of random values and bins. This returns a tuple, which we can unwrap into the histogram values and bins. And then we'll play around with this a little bit. So simple histograms now in matplotlib can be plotted as follows. So by calling the stairs function and passing the unwrapped histogram tuple, or you can pass them separately. So in this case, I pass the values separately and add a shift for the bit values. And there are some options that follow, such as changing to the filled histogram type, and this also is propagated to the legend subartists, which was problematic to do only with MPL HEP. Oops, sorry. However, as I've said, there is space for extending this functionality for further uses that are more domain specific. So the glaringly obvious one is plotting histograms with error bars. So in this case, you can pass wire equals true, and this will calculate some kind of automated error bar. So this should be, I think, Poissonian. But you could also specify directly a specific value, or you could use you could pass the sum of the weights squared along with the function call that would take this value into, or that would calculate the error from any prescription that would be desirable. So the primary goal is to stay as unobtrusive with this as much as possible, as if this would be part of matplotlib. So any keyword arguments that you are used to from matplotlib should also work just as well. So the hist type should be fairly intuitive, but it is modified. But all the values that you might pass to the underlying matplotlib object are simply passed through and processed. So color, you can select the hatch here. On the error bars, you can select the cap size, etc., etc. Oops. And again, in the same spirit, we want to be able to do exactly the same thing as plot hist or pyplot hist. So if you pass an array of histograms, you can then stack them or take the density on both of them. Or you can apply a dedicated norming factor to both of these. This is useful if you want to do somewhat more complicated things. So in this toy example, we take those two histograms, and then we generate another one. This will be a Poissonian redraw from the values, which would be something like data. And as follows, we could plot a data MC shape disagreement. So by taking the density of the stacked plot of two MC samples compared to another plot of what would be our data, we create this comparison, which seems to come up a lot in our line of work. We also want to be fairly flexible about the input types that can be used. So in the first plot, this takes a simple list of values. The second plot, it takes a tuple, or it takes the unwrapped values and the bin edges separately. So this is convenient when one tries to debug things very quickly, or works with various types of input data. Thanks to Henry's implementation of the UHI, we are able to process essentially any any histogram object that implements the plottable protocol. So in this case, this is an example of loading a root file and opening it with uproot, and then passing the th1f object to histplot gives you the plot without any further effort on your part. Thanks to a recent pull request from Pieter, I think, it is now actually possible to pass a PyRoot histogram into the MPL-HEP function, because the plottable protocol was implemented for this in the UHI, so you can actually pass a PyRoot th1 into histplot and again get the nice result.
2-minute warning.
Oh
Maybe
yeah, I see. Okay. So yeah, one of the further things is to integrate very tightly with PyRoot. So, sorry, pardon me, with hist. So passing the hist object, it picks up the label. I'll go quickly now. It will also pick up for categorical access. It will pick up the separate labels for the bins. If you, and these are unsorted because this is a drawable access. If you passed an array of categories here, this would be in order. 2D histograms are also implemented, which are a little bit easier. So there's a minimal rep on p-color mesh, mostly just flipping a couple of things. And so again, this is an example from hist, and an example from a plot from uproot. More importantly, we have the collections of various styles. So this would be what an default Atlas style looks like. We have a default CMS style, LHCb style, which is default a little bit larger figure size, and analysis styles, which were all contributed by developers from the separate experiments. We also have default experiment labels, which seem to come up in the common location when they would typically be. So if you replace this for Atlas, you would get an alternative plot that looks like this. And that actually hopefully fits me in the last 2 minutes. I had 2 extended examples that you may look into later, as these are some things that come up or have come up in the past quite often. But the one that I would like to.
Actually, we're running out of time now.
All right. Well,
there is one question. So just the one question before we move on to the next speaker. And then the other questions, remember, we go to Slack.
Yeah, let me, where's Slido? Here.
I have a link in the Zoom chat.
Well, as MPL hist object with non-regular axes. Yes, that's not implemented currently.
Okay.
Yep.
Thanks. Follow up on Slack. Thank you, Andre. Next lightning talk is PyBump Hunter by Louis. Are you here? Yes, you are.
Yes. Hello, can you hear me well?
I can hear you. Can you share screen?
Yes, sure. I share my screen.
Mm-hmm.
Okay, can you see it well?
Yes, that's perfect. Thank you.
All right. So, hello everyone. Thank you for being here. I will present you my PyBump Hunter tool, which is a model agnostic bump hunting tool in Python. You can find it on GitHub and also on PyPy, so it's pip installable. So first, a little introduction about the bump hunter algorithm. So this is a useful algorithm used in the energy physics community that allows to look for an excess or deficit in data solution with respect to reference background, and also computes the local and global p-value of this localized deviation found in the data. So this bump up is done by scanning binary distributions. So it's a histogram-based method. As you see on this picture, you have a background and data histogram. You have a scan window with a variable width that scans over a spectrum and tries to find the interval for which you have the most significant deviation. So this package is inspired by the original bump filter algorithm, which is described in this paper. So little word about local and global. So local p-value tells you that there is a deviation, but it doesn't tell us how likely this observed deviation is to be a statistical fluctuation. So to say that, the filter generates toys from the reference background and scans them like a normal data. This will give a background-only local p-value distribution. This is what we can see on this plot here. This p-value is turned into a buffer statistic distribution. So we have the pseudo data which correspond to the background-only distribution, and the data which correspond to the observed data. And with that, the global p-value is then defined as the p-value of the local p-values. So why PyBump filter? So I decided to make this package because it's allows to have a public implementation based on pure Python. So by pure Python, I mean mostly NumPy, SciPy function, and it doesn't depend on vote. So if you want to move away from vote, it's nice. And it was recently integrated into scikit-learn, and it's still under active development. So for the features that are currently available, we have scans for 1D and 2D distributions, also signal injection tests in 1D, as well as a sideband normalization feature. So I will present briefly on this point. So the 1D scan, so this is a basic scan that compares the data to a distribution to reference background. It gives you the position and width of the bump, as well as the local and global p-value. It also gives a root evaluation of the signal content of the bump by computing a data minus reference in the bump window. So for that, what we do is we generate some data. So we have a background histogram, observed data with a little bump, which is localized here, but we can see it like that. And that what we do is that we create a bump filter 1D instance. We give it some scan parameters and number of pseudo experiment, binning and range of the histogram, and so on. And then we call the scan function that will do the scan over the data and all the toys. It takes a few seconds to run. There it is. So now we can see the results. So there are 3 plots available. First one is what we call the tomography plot. This shows the local p-value which is computed for all the intervals that are tested. And here we see that the best interval corresponds to the one that has the lowest p-value. With this interval, we can have a distribution plot with the bump highlighted here, and with the significance map, which shows you the local significance per bins. So we see that the bump corresponds to this excess here, which is located where I was expected to be. And we also have the bump statistic distribution with the toys in blue and the data in red. So this is for a symbol scan or both signal injection. So this is a bit of an extension of the possibility offered by the 1D scan. In fact, this has the possibility to perform signal injection tests using bump filter algorithm to evaluate the sensitivity of a given signal model. So the injection is performed based on the reference background and the data distribution and the signal distribution that you want to test. And the injection stops automatically when you reach sensitivity that you want. Currently, this is only implemented in 1D, but might be extended to 2D. So here I will not run it live because it will take a few minutes, it will be too long. But what we do is that we generate some normal distribution for the signal. We define some injection parameters and we do the scan. So what the algorithm does is it does some background on the scan and then it starts the injection on the first background and do some scans with injection. It goes on until we reach what limit we want, and we get this plot as results. So in order to obtain the error bars, what we do is that we generate some background plus injected signal toys. This will give us a global p-value distribution with a median in the first quartile and the third quartile. This is how we obtain this error bars. So this is for the injection. So now, well, I will answer the question at the end. About the 2D scan, this is an extension of the bubble algorithm to 2D distribution. It works the same way as in 1D. And as far as I know, this is the first implementation of the printer in 2D. So what we do here is exactly the same, but with 2D distribution. So we generate some 2D histograms with some signal which has been injected here. And to treat that, we have a BumpHunter 2D instance, which works the same way as the 1D, but with the 2D parameters. And the same way we can call the bump scan method in order to do the scan and generate the toys, and we can plot the results. So there is no tomography plots in 2D, but the result obtained here is that I have now my distribution with the bump, which is highlighted. So it's close to where I was expected to be. I also have the local significance map that shows local significance per bin, just like in 1D. And I also have, again, BumpHunter statistic distribution.
Quick mention that this is a 2-minute warning. You have a 2-minute warning, and you've got questions coming.
Yeah, I can answer the question now, you mean? So the exact p-value definition, so local p-value for an interval is based on the gamma functions when you, that takes number of events in the data in the background. So I don't have the exact definition here, but you can find it on the paper. And those who want to move away from root, I would not say that moving away from root is necessarily a goal, but it's just that in many workflows we use a lot of Python. For example, if you want to use some machine learning based stuff based on the TensorFlow and so on, you have a workflow which is in Python, and it might be tricky to move back from Python to root and so on. So this way, it's you can simply continue workflow in Python. This is what I meant there. So I don't know if it answers the question. Let's move to the sideband normalization.
Okay.
So this is
just about ran out of time. So if you could conclude, that'd be great.
Yeah, I will be quick. So sideband normalization. So this is an option that allows you to automatically rescale the background when you do the scan. So in order to, for example, this example here, you see that there is an offset between the background and data, and background normalization will allow you to compute a normalization scale for each interval which is tested, and this can be done automatically during the scan, and can also penalize p-value when there is a discrepancy between data and background outside of the scan window. So here I will not run it, I just show result. I generate this. I create a BumpHunter instance with this option enabled. And when I see the result, I see that it has been rescaled. So since I'm running a bit late on time, maybe I will not present too much the multi-channel combination. This is something which is planned for the next release. I have two combination methods for to combining multiple channels and have a combined p-value, but I will not go in detail to this. So for future plans, for the next release, we have this multi-channel combination which is planned. Also, future things which are planned are an API refactoring with a data render class that manage the histogram parts separately from the scans, and also add possibility to treat systematic uncertainties and other features as well. For that, your ideas are of course welcome. And the paper presenting the new features in detail will be is in preparation. That's it from my side.
Great, thank you. Any further questions? Take them to Slack, and please do. We want to encourage follow-up discussions there. So if you didn't get your question asked, please go there.
Okay.
Thank you, Louis. Next
Thank
is Xiangyang talking about route to GNN for HEP data. So great, thank you. Go for it.
So I prepared this notebook. I will just go through the notebook, and I also post the code to the link. So this is basically the a tutorial notebook we prepared to get to help the users get started. But we also have a detailed description of the how to run the package in terms of the command lines, how to install them, and a detailed example to use the supervised Jita clustering method. And the data is also prepared, and we have commands how to get the reproduce the results that we published with this package. But without further ado, I will just briefly talk about one possible way to use this package in a notebook. So the overall goal of this package is to facilitate the training of the graph neural network. The graph neural network is very flexible, so there are like many possible combinations or the way you can construct the graph neural network, but we just like try to connect the models that are proven or has been used in physics publications and in this repository, and also writing the code to monitor the matrix for classification and regression tasks. Later, we are going to add also that like a generative graph neural network based models in it. So the graph creation, there is basically two ways to do that. One is based on this NetworkX package. To do that, is just define the graph and add a nodes, add edges. For example, I just add a node, 4 nodes, 0 to 3, and edges I just connected them in this way. You can make a plot like this and visualize it. This is called a directed graph. You see that the point node 2 is pointing to 3, 3 pointing to 0. This is directed, and you can do bidirectional so that the message they can pass through all the directions. The graph that normally we use is an attributed graph, meaning that the node has attributes. For example, node features. This node could be particle and has 4 vector, for example. And edges can also have their own attributes. For example, this can represent the distance between the 2 particles. Another attribute is the graph level attribute we call global attributes. That can be like event level information, could be part of the conditions or number of particles in the event. To represent this, attributed directional graph, one can use this adjacency matrix to represent the edges, how the particles are connected, or a preferred way to construct the graph tuple is use a data dictionary. So the keyword we are using is following the GraphNets from DeepMind package. Basically, we want to know how many nodes are there in this graph and how many edges, and the node attributes. So this will be with a dimension of number of nodes times node feature, number of node features, and similarly for edges. So this will be number of edges times edge features. Senders and receivers are basically to define each edge. So each edge, like which 2 node is belong to that edge. Global attributes is basically the global features of the graph. Once you have this data dictionary, you can just convert them to a graph. So in this tutorial, we take an example from a top tagger data set. You can download it from here, and I already downloaded it in local. I cannot run it in Biome because this more than 2 gigabit. But the data looks like this. Like each row is a one event, and each particle has 4 vectors information. So this is the particle 0, this is particle 1, and so on and so forth. I can just loop over. I can take like a one event, one row, and try to make a graph. because I know that there is how many features in the event, I can just quickly go over all these items, all these 4 pods to get the particle information and the particle 4 vectors. That's what be my nodes, and my edges is just fully connected edges, bidirectional fully connected graph. In the end, my goal is to tell if this event is a QCD event or top quark event. So in my target graph, so this is my input graph that's basically have the particle information, but in my target graph, I tell this if this event is a 1 if it is the top tagger, 0 is if it is the QCD event. So I call this function to make a graphs, and I can visualize, check the dimensionality of the graph, and if it's set to make sense. In the end, you just need 2 functions. One is called read, the other one is called meta graph to construct a data set. And this data set, once you define it, you can process the whole training set with to convert them to a native representation of the graph in TensorFlow. That can strongly facilitate the training speed. So I have done that, and once we have, and this is like process will save all the TF records, that each record contains a certain number of events in each TF record in this folder. And then I just split them for 80% for training, 10% for validation, and 10% for testing. We have predefined models. I just go to the way that you would use them in here. So you can just take all the models, choose one of them, say global classifier, and define a loss, that global loss that you basically for classification, and define on optimizer. Once you have that, you can put them in all in a trainer. So the trainer we have many like default values one can just use as these, but we also provide the handles to tune some hyperparameters once you find the results is not optimal. Once you construct the trainer, you can just start training and monitoring the status. So this is just one way to monitor. We also have the backend in TensorFlow. So in this output, there is also directory to monitor all the metrics that for the classification and regression. Yeah, that's the tutorial. Thank you.
Okay, thank you. On Slido at the moment, there are no questions, but we'll be following up on Slack, as always. Next is Jay Yang talking about HepiNet. So,
yeah, let me share my screen.
Yeah.
Okay, can you see it?
Yes, we can see it, and we can hear you. So great, go ahead.
Okay, so so today I'd like to give an introduction about the idea of HepiNet. So it's designed to be a neural network assistant framework for high-energy physics analysis. First, what does this name mean? So it means the high-energy physics Python-based and neural network assistant framework. And then what does HepiNet do? So the major feature are 3 things. One is that it's targeting high-energy physics analysis. So it's trying to perform typical MOA studies in physics analysis with neural network. And it's config-driven because all the tasks are defined by simple configs, actually no code needed for the neural network. And the codes are written in pure Python, and as Python is a mainstream language for neural network study right now, it will help us easier to use the new packages that come out that may help us in some aspect. And currently it's based on Keras with TensorFlow backend, but in the future we're considering support other frameworks as well. And the goal is that we want to quickly set up the new studies or analysis without read any code as users, and we can have a good record of neural network study history because each config file defines a study, and if we want to compare two different studies, we just compare the config. That will already tell what's changed. And another thing that we can have shared efforts from different persons as the functionality developed by one person that can be easily applied to another person's analysis easily. Usually just add a few lines of config files. Like in this picture, I shows the basic workflow using the HappyNight. So first you will have some convert the root files with uproot to the pandas data frame, which is the default format in HappyNight and currently, but we are constantly support more formats, of course. And then the following steps are all defined in the config files. We need to have some pre-processing, like we want to normalize it with mean and standard deviation, and we got inputs. And then we can first to do some manual tuning. We can try different setups to do the training and see how it works in the end. And after a few times, we may have an idea what kind of value that makes sense to for the hyperparameters. Then we can go to the auto tuning, and here we just set up the algorithm, like for example Bayesian, and then set up the search space. Then it can automatically tuning the hyperparameters with the iteration itself. And in the end, once we got the optimal models, we can try to see the performance as well. And like we can have plot the basic DNS score. We can check the ROC and other metrics. And also we can produce the input for the fitting framework, and we can check the feature importance with permutation method and so on. So this page shows the core package used in HappyNight right now. So for data processing, we are using uproot and pandas for management. And for the training, we currently use the Keras with TensorFlow backend and use sklearn to help some processing in some space. And for the tuning, we are using the retune, which can do the experiments of different hyperparameters at any scale. And for plot, right now we are using just basic matplotlib, but I saw a good package that PyHEP today. Maybe we can use that in the future for better and easier plots. Like this page shows the core concept, the config files that defines a job. So we currently use YM format, and we have 3 different type of configs. Like we have train, one type for tune, and also for apply. And in total, we have 6 sections plus 1 run section that manages at the running time. And we can see some examples here. Like we have these 3 sections are some general settings for different job types. Like we can first including some dependence config files, and for job section we can have some general settings like the specified job type and the save directory to save the outputs, and also sometimes you may want to set up the random seed as well to have a repeatable result, and that also can be done in the job section. And in the inputs, we specify the source of input, and we want to specify what kind of features we want to use, what kind of process we want to include, and what kind of pre-processing we want to do. Like we can have a normalized array, and we can also have some scale of the training weight. And also we can here we can reset features that's mainly for the parameterized neural network. And for the training is quite straightforward. Here we just have some model class developed for the different high-end physics tasks. And then you just put some parameter that's just basic Keras parameters, and you specify here, and the code will read it and to do the training, and you set up the early stopping as well, the metrics you want to monitor as well. And then for the tuning here, So here we want to do a automatic hyperparameter tuning. We need to set up the algorithms, and as the array package support many other algorithms like the Optuna hyperopt Bayesian. So basically, it's very flexible to choose what you want. And then you set up a search space as defined here. Basically, it's just a similar set configs like the training config file. So you set up different hyperparameters, but one difference in that in here you can set a fixed value, but you can also set up a spacer, set up a dimension here. For example, here you set a dimension between 0 and 0.9, and then later the algorithm will do a scan at this dimension, and you can specify multiple dimensions as well. So that makes our search space a multi-dimensional space. And in the end, after we finish the training and tuning, either by hand or automatic tuning, we want to look what it looks like, and we can book different studies. Like here, we can check the history, we can check the kinematics, and check the MAV scores. Yeah, and also we can check the kinematic before and after some DN cut and also importance studies. And this, okay,
it's
yeah.
2 minutes.
Yeah, and this is some examples of I got from real analysis currently, and I see, for example, the top left one shows some metrics that you booked during the training, and you see how the metric changes when the epochs increase. And here is actually include a K for the training as well. And the top middle one is some score distribution of different process. And top left one is the important studies that tells you which features may more important to your deep neural training, and you can remove that not important features in the future training. And yeah, and bottom left, I show some kinematic before and after cuts, and the middle some significant scan, and also some correlation studies as well. And so for the summary, the HEPnet is being developed to help set up deep neural studies in high-energy physics analysis with simple configs. But the development is still at very early stage. It's currently being improved based on the usage and several ongoing analysis. And some of them is at the EB stage. I think that will help a lot to us to improve the HEPnet. And also the suggestion and joint efforts for development as user or developer at this early stage is really welcome and appreciate. Okay, that's all. Thank you very much.
Speaking of suggestions, there are 2 questions on Slido. Could you share the Slido screen so that we can see the questions, you read them and answer? So make them big, yeah. Right.
Oh yeah, first for Jason, yeah, at the beginning actually I was using JSON and also the initial format, but later I found is doesn't have very, it's not easy to use, especially when you have include some dictionaries and lists. So and when I use the YML, it's very easy to process everything I want. So in the end, I choose to use YML, but yeah, I think this is okay, just as long as it works. And for the second question, how many hyperparameters are tested during the optimization by default? I remember the default value is 100, but you can set up yourself. Usually I will do a 1,000 or a few hundred scan for the hyperparameter over auto-tuning.
Okay, thank you. The last talk is Andre talking about NatPy. So Andre, are you there? Andre? can you share your screen and say something?
Hello?
Okay, I hear you very faintly. If you can get closer to the microphone or increase the gain or something.
Is this better?
It's a little better. It's still quiet.
You're quiet? Okay, let me increase the gain.
And also share screen.
Yeah, we'll do. Is this better?
Maybe turn it down a little somewhere in between.
We've gone too far in the opposite direction. Okay, how about this now?
That's great. Thank you.
Okay, let's go here. Okay. Can we all see this?
Yes, I can see it.
Okay. Hi. So today I'll be discussing NatPy, which is a simple package that we've made for dealing with natural units in your Python code. NatPy leverages AstroPy and NumPy, and you can get it through pip. So to start with, has anyone ever wanted to convert MeV per femtometer cubed to, say, pascals? Well, now you can. Just simply define a unitful parameter after importing NatPy, and we can do that like so. And then we can just call NatPy's convert method, telling NatPy exactly what units we wish to convert our expression to. And there we go. So in high energy physics, this is not anything new, but of course, the standard convention is to set h bar equal to c equal to epsilon not equal to 1. And what this does is implicitly rescale our physical quantities, okay? And so the fine structure constant becomes 1 in 137, the electric charge becomes scalar, mass, momentum, energy, length, cross-section, time are all measured in various powers of GeV. And to recover these SI quantities, we have to insert certain factors of h bar or h bar c or h bar c squared, etc., or c squared. And so that's where NatPy comes in. So NatPy quantities are AstroPy objects, and we can easily access all of AstroPy's constants easily, like so: speed of light, h bar, the electric charge. And so now where NatPy comes in is, if say I wanted to convert the electric charge to its natural unit form, I would again just call the convert method, specifying that I want the new dimension to be unitless, which we've called 1 or nat.1 for short. And as you can see here, we just recover what we saw before up here. Okay. And so, converting single quantities is easy, and that's all well and good. But how does a real world example look? A physics analysis, in a real world scenario. And so I've just cooked up something here. So consider calculating the average decay length of some new physics. Okay, so we've got some equations. The average decay length, goes with some Lorentz factors, and it goes as 1 on the decay width. The decay width is given down here. I've got some heavy new physics Chi2 decaying to some lighter particle Chi1 and some leptons. Okay, so just a typical inelastic dark matter type scenario, for example. This process is mediated by some heavy vector MA prime with mass MA prime. But at the end of the day, there are some equations. We have some quantities, they're all unitful. And this is all well and good. So, this is all in natural units, fine. But let's say we're an experimentalist and we want to, say, calculate some sensitivities for some future detector or something like this. We may want this, we may want to calculate this decay length in meters or centimeters, kilometers, if you're doing non-baseline stuff. And, you might be able to look at this and just see what you have to do to convert everything from natural units. But, for things that are more complicated, it might not be so simple. But, just as a kind of hello world example, we'll go through and calculate everything here. So I've just defined a bunch of my model inputs here. Okay, so again, I'm just going to define my masses in natural units. So this, the mass of this Chi1 is going to be 10 GeV. For reasons, the mass of the vector is 3 times that, and I specify this mass splitting delta, the mass of this Chi2 and the other model parameters epsilon, this alpha dark. This alpha EM is the fine structure constant, which we'll use NatPy as just constant intrinsics for this. Okay, so this is all in natural units, and so everything's easy now. I can just basically code this up verbatim, and so that's what I've done here. You know, I've calculated the decay width, which is a function of these model parameters. You can see my Lorentz factors, beta, and the boost factor. The boost factor for the record being calculated in natural units because I can. And eventually I've got my decay length here, and so I can do that. Now, this is going to be a function of the decaying particles 3 momentum, which let's say is 7 GeV, just as an exercise. And if I execute that, you know, I get an answer as I expected to be in inverse GeV, because my decay length goes as 1 on gamma. And gamma is, as everyone knows, is in natural units at GeV. But, you know, this might be good for most people, right? You might see that, okay, inverse GeV, I know what I have to do. I can go back up here. I see that it's a length that I want. And so I just insert the relative, required factor of H bar C, and I'm good. But we've got NatPy, so we'll just use that. And we can, again, call this convert method, telling NatPy that we want our answer in meters. And there we go. And so the point is, as long as intrinsic natural unit consistency is achieved in our code, we can always convert the final result or anything in between actually to whatever units we want, as long as it's all consistent within our specified units. And so to demonstrate this, I'm going to do something spicy. I'm going to say, hey, let's in fact define my mass of this lighter particle in kilograms. I don't know why you'd want to do that, but let's just say we do. Okay, so a 10 GeV particle is about 10 to the negative 26 kilograms. What happens if we rerun this guy? Well, I recalculate things and okay, we get a slightly funky answer. We've got this prefactor here, which is quite large, and NatPy has just carried through all of the units, and we've got something in GeV to the power 4 on kilograms to the 5. Okay, not very useful. But again, we can just use NatPy, tell it we want everything in meters, and we get exactly the same answer. This is a very simple example, but as you can imagine, if things are very much more complicated, it can very quickly start to become the case where we start dropping factors of H bar or C, you know, or just even scale factors, you know, kilograms to grams or you know, GeV to KeV. NatPy handles everything as long as we specify the units to begin with, and our equations make dimensionful sense. Well, that's not all. By default, NatPy ships with a bunch of unit conventions. The user can specify their own. By default, we have H bar equals C equals epsilon naught equals 1, but we can set our active units to be Planck units. And this little example here lets us recover the Planck length. And so what I've just done is convert 1 to meters, right, which in Planck units just gives us the Planck length. So that's it. That's basically all I wanted to get through. And I'm not sure if I have gone over time or if I'm hearing the cue.
I was just going to give you a warning, so you're perfect.
Yep. Okay. Good for time?
Yep, good. You have 3 questions. If you could share the Slido in a tab in your browser, make it big and read the question.
Make it big and read the question. Okay. Okay.
Control mouse wheel.
Yeah. My computer doesn't want to do this. I'm sorry. I'll just read them perhaps. Okay. So the first question here is from Jim. If any quantities in natural units are extreme floating point values, exponents abound around plus or minus 100, do you see numerical precision issues? Potentially. You know, I haven't broken it yet. Everything I've used NatPy for has so far worked well. Again, I don't use anything with these large components, but again, I can't really tell you because I haven't done the testing. I don't see it happening because I haven't experienced this myself. Anonymous says, can these units be made to work inside NumPy arrays, or is it limited to individual values? Yes, so they can work in NumPy arrays. Where do you get your constants from? Any chance you can sync with HEP units? I don't know about syncing with HEP units, but we get them from AstroPy.
Okay, great, thank you. Any other questions can go to Slack, and please do continue the conversations there with all of our great speakers. And everybody be under reactions on the Zoom. You can clap for everyone. And it was a great day today. See you tomorrow.
Bye, everyone.